advertise this to other people or other academies or something like that?
Yes, Professor Ghatak, I've actually emailed maybe a total of about 1,500 people globally.
Oh, I see.
Which essentially covers pretty much all the continents. I had actually organized during COVID a few online lecture series called Mysteries of the Universe, MOU 1 and 2. And MOU 2 was done in collaboration with Professor T.V. Ramakrishnan. And so that also helped us generate an email list. So that was pretty handy.
So Dr. Panchapakeshan has just joined, I think, because I see Nargis's iPad.
Yeah, I see that.
Yeah, it's there for a bit, but I'm not sure whether... Hello, Professor Panchapakeshan, can you hear us? Not sure. I must say I'm getting a little nervous. Let's see. I can see, I think he's probably speaking because we all see, you know, the relevant indication. But can you do something about it? I don't know. Didi, could you kindly call Professor Panchapakeshan and ask him if he's facing some issues? I mean, because he's our first speaker and we are gradually moving towards the start time. Can I ask you humbly to please, Didi, you're muted. Oh, Didi, you're muted. Let's see.
I'll just log out and log in back again.
Acha.
And I'll call him.
ठीक है.
Because I'm calling from my phone.
Yeah. Now we see him. Oh, lovely. Yes.
Recording in progress.
Professor Panchapakeshan, can you hear us?
Hello, good morning. Can you please?
Eddie.
I think there is a problem with Zoom that if you log in through multiple devices for the same meeting, there would be an echo.
Hello. Can you hear me?
Yes.
No, I can see. Can I start? Can I share the screen?
So I think we are 9 o'clock. So I think I'll just say the following. Welcome to the A.N. Mitra Memorial Meeting and Lecture, and which is jointly organized by the former students, collaborators, and colleagues of Professor Mitra, and also Gargi Mitra Delmot, his daughter, and a very extremely indebted and grateful mentee. So this, I think, is a celebration of the life and especially the physics done by Professor Ashoknath Mitra. And I'm I'm no Sanskrit scholar, but I would succumb to the temptation of saying that Professor Ashoknath Mitra is Guru Brahma, Guru Vishnu, Guru Devo Maheshwara, Guru Sakshat Para Brahma Tasmai Shri Guruve Namaha personified. With that, I would request Professor Nimai Singh, the chairman of the free lunch session day 1, to kindly take over. And Professor Nimai Singh, please.
Yes, Professor Alok, thank you. My name is Ngangkham Nimai Singh. I have been given the responsibility to share this first session. And it is a great privilege for me because Professor N. Mitra was my guru and my MPhil and PhD thesis supervisor. In addition to that, the first speaker of today, Professor Natarajan Panchapakeshan, is also my beloved guru in MSc during my MSc. And I still remember that Professor Panchapakeshan is famous for his high humility and soft speaking. I observe his close relationship with Professor Mitra and mutual respect among them. I request or serve Professor N. Pacification to start the talk. We have 25 plus 5 minutes, 25 for the delivery, 5 for the discussion, total 30 minutes. That is the thing. Thank you, sir. Please start.
Professor Panchpakeshan, would you want us to handle your slides or?
Yeah. Can you bring the slide up?
Yeah, sure, we'll do. So what we're going to do is we are going to share your slides, and whenever you want us to go to the next slide, just kindly say yeah, the next. So we'll go to the next slide. Yeah. So I'm sharing. Just a moment. Just a moment. Just a second.
Yeah. Can I have my slide? Oh.
Just a moment, please.
Oh.
Okay, so can we all see Professor Panchpakeshan's
Yes, now it is all right. It is all right.
And
all
I
right.
think, let's see, I thought I went full screen. Yeah, I think now it's in a full screen mode. Is it okay now, Professor Panchpakeshan?
Yeah, okay.
Welcome all to first lecture. Can you hear me? Can you hear me?
We can hear, sir. We can hear. No problem. Now,
But
please
there
start.
is an echo because there is another. Now it is muted. Okay.
Okay. Okay, let me welcome all to the first N. Mitra lecture. I have already written about Professor Mitra several times. The first one was in 2014 when I wrote for the Current Science. Next one was in 2023 when he died. I wrote for the Hindu journal and the Current Science. I referred to the ideas of Professor Mitra on religion. Even though in the year 1975, Professor Mitra and I were invited by George Sudarshan to come and attend the meeting of Mahesh Yogi. Anyway, let me now use some of his own writings to talk about Professor Mitra's talk, views on religion. Mitra likes to begin with Cartesian partition. This is the Cartes who started the Cartesian orthogonal coordinates, which are the XYZ coordinates, and as different from R theta phi coordinates. And René Descartes was actually a philosopher as well as a scientist, but he laid down a partition, which is often called the Cartesian partition. And this partition was that religion should not be part of science. Probably he did this to make faster progress in science because the discussion of religion can go on and on and on and goes off all the time. So this would help the science. Thus, in spite of the views of Kepler and Newton, this partition somehow took effect. I'm saying this because Newton was a great believer in God and he believed all natural laws were due to God. And Kepler also thought there was a natural order which brings its loss to science. J.N. Mitra quotes G. Holton to say that the theory versus experimental proof is the proof of the scientific method, is the basis of the scientific method. And from almost 1660 to 1900, this partition worked very well. So for almost 250 years, it worked very well. But unfortunately, when the 20th century began, there was a big problem because the relativity came in, the arrival of relativity, which made time relative, and quantum mechanics, which made causality statistical, diluted determinism, and changed the whole picture. And by 1930, everything was total chaos. This is because quantum mechanics brought in participatory physics, and the effect of which cause finite is very, very important. Time in relativity, time is relative. It is important if a velocity is comparable to that of light. In quantum mechanics, photon and later electron are both found to be particles, localized, as well as waves like Atma and Paramatma in religion. Causality and determinism both become statistical. Individual event cannot be predicted. Einstein thought quantum mechanics is incomplete. Bohr, with his complementarity, argued that one can do no better. Unfortunately, we still have no agreement on what is really a complete theory of quantum mechanics. F. Capra compared the universal and self-interaction in quantum mechanics to unity in the universe experienced by mystics. On that basis, he thought bootstrap theory should be correct. Unfortunately, he turned out to be wrong because it is quark model as fundamental particle, which came into prominence, even though the quarks cannot be observed individually. Maybe instead of mysticism in science, we need science in social science. And in our lives, we really have a lot of emotions. Our lives are full of emotions, love, compassion, joy, ecstasy. And so it is really the other way around. We need science to come into scientific temper or mysticism. To discuss this, I must go back, rather I must go to a philosopher called Ronald Searle from University of California, Berkeley, who gives what I thought was a nice separation of natural science from social science. He says natural or God-made laws are in natural science, and man-made laws like marriage, justice, income tax are in social science. Scientific temper, which applies rationality and logic to life, then becomes a social science. It has huge error bars, no agreed axioms, and requires immense tolerance or alternative views. Now, Professor Mitra has written a number of articles on
Professor Panchpakishan, I really
science and
apologize to
religion.
interrupt you. Professor Panchpakishan, I apologize to interrupt you. Could you also kindly guide us? What slide number are we at right now?
Oh, you want me to go back? Okay.
No, what I mean, I assume we are now on slide number 2. We were waiting for you to say next.
Okay, one moment.
Just to correlate what you're saying with what is visible.
Maybe I can end the show and start again.
No, you don't have to. Just let us know what slide number should we be showing.
No, do you want to show my picture also in the screen?
No, it is visible. It is visible. Just let us know the slide number. Like,
so should I go on to the next slide or the previous slide?
Okay, what slide number are you currently at on your screen?
I am trying to have the earlier one.
Oh,
yeah, this one. This is the one that I want to have.
Okay, great. So when you want to go to the next, kindly let us know that you'd like to go to the next, and then we'll immediately go next.
Pardon, I didn't get what you said.
So when you are done with the slide and you'd want to go to the next slide, please let us know so that we can click next and go to the next slide.
Okay. In this slide, I have listed the references of Professor Mitra. As you can see, the references started quite early. In the year 1986, that is reference number 2, he wrote an article in Pramana on duality in physical sciences and beyond. This was his first entry, I think, into print of his views on religion. And then in 1990, he wrote for Physics News something on parameters of physics perspectives, principles, and postulates. This was actually a talk he gave in Delhi University's Department of Education, where my wife Nargis, who was also a student of Professor Mitra at one time, had invited him to give this talk. And then he wrote a much bigger article in 1993 This was in Current Science. And then he wrote a foreword to the book by R.S. Kaushal. The book was called The Philosophy of Vedanta, a Modern Scientific Perspective. And I have really quoted from this book about the partition and other things he talks about. But apart from all this, I must also, while I'm giving references to Professor Mitra, should talk about a very, very good book, which Professor Mitra edited and published when he was 80 years old in the year 2009. It is called India in the World of Physics Then and Now. It is published by Pearson Education, and it is part of a series of books called History of Science, Philosophy, and Culture in Indian Civilization. It has got very good values, very good reviews by experts. It has a very good review by Professor T.V. Ramakrishnan also on condensed matter physics. And it begins with a remarkable photo in the beginning by Jean-Jacques and Gargi Delamont of the areas of physics covered after the independence in India. Gargi quotes also a couplet by Tagore, which is very interesting. In Bengali, it says, Simar Majhe Asim Tumi Bajao Apan Sur. In English, the translation is, amidst the finite, the infinite you, play your own tune. And so I would you see, this book is fantastic, but I find it is only in library and hardly anybody refers to. Maybe some people should take parts of it and write about it in Wikipedia or something like that. Yeah, I finished with this slide now.
So we're now on the slide which reads relativity and Q mechanics in 20th century.
So should I press something or you do something?
Is this the right slide? This is the one that you'd like to be at?
Shall I go to the next one?
No, Professor Panchakeshan, the slide that we are currently at reads as the header, relativity and Q mechanics in 20th century. Are we on the right slide?
Shall I go to the next slide and talk? That may be simpler, huh?
You want us to go to the next slide?
Okay. The next part of my talk is really about black hole QNM, quasi-normal modes. And before I go to this, I must say that I heard something which many of you must also have heard, that if you make a better mousetrap, the whole world will make a line to your house. So this work of ours is also a bit like that, improves something and gives a calculational tool. Let me first give a brief introduction to black holes. Black holes came into astrophysics in 1931 when Chandrasekhar showed that white dwarfs have an upper limit in mass. Later on, it turned out to be true for neutron stars also. So if a star has a much greater mass, it cannot become a neutron star or a white dwarf. So it must become something else, which we now know are black holes. But unfortunately, nobody believed in black holes, especially Eddington, who was Chandrasekhar's supervisor. And because of that, nobody did much work on that. But long period later, Wheeler and his group in Princeton and groups in Soviet Union did a lot of work on this. And in 1972, Misner, Thorne, and Wheeler summarized the status of the subject in the book Gravitation. By that time, quasars were identified as black holes also. From India, C.V. Vishweshwara was the first person to work in black holes, and he did some very remarkable work. He proved the stability of the black holes in 1970. He also calculated the quasi-normal modes of black holes, though he didn't call them quasi-normal modes at that time. These are the typical signals observed in gravitational waves when they are observed in 2016. Much, much later, Vishu died a year later, so he really couldn't enjoy his glory of being the first one to give this particular signal. Chandra came back to black holes in 1960s. As usual, he ended up by writing a book on mathematical theory of black holes in 1983. Now, stability in black holes and elsewhere is studied by perturbing the black hole metric and seeing if the added signal is damped and dies out, emitting what are called quasi-normal modes. Solving the perturbed equations by separating the variables is an arduous mathematical job. In 1971, maybe I'll come back to this. Sorry. Yeah, in 1971, at Delhi University, Professor S.N. Biswas, who was also a towering figure in the Delhi University, and 4 other very talented youngsters wrote a paper in the Physical Review in 1971. The collaborators were Kamal Datta, who got his PhD from Brandeis, R.P. Saxena, who was the first student of Professor Mitra and wrote a big fat thesis on meson renormalization. And then Pramod Kaur Srivastava, absolutely brilliant person, who, along with Vijay Verma, both moved into science education later on and were supporters or founders of the Hoshangabad science teaching program. These people got together and wrote this paper, which really shows it is called the Hill determinant method. And a general differential equation, when expressed as an infinite sum of constant coefficient, gives a recurrence relations. The boundary conditions satisfied determine a 3-time recurrence relation. Hill determinant can be written down once the recurrence relation between constants are known. The vanishing of the Hill determinant helps in finding the eigenvalues of the solutions, which are the quasi-normal modes. We can call this the Delhi University Hill determinant method if you want. Till an improvement is found, this can serve as the method for the moment, but I was surprised to find in the program, we have another talk by Jatu Kunz from Germany, who is talking about this method again for a special class of metrics. That will come tomorrow in the afternoon. This was Bhavani's PhD thesis. And Bhavani Majumdar and I, in Physical Review in 1989, applied this method to QNM. It is said that people will queue up in front of your house if you build a better mousetrap. So that paper now has 50 citations. It's not a very large number, but very surprising to us. The cited papers all use this method successfully. Well, I come to the end of my talk. Oh, is it 20 minutes or 25 minutes? 25 minutes I'm given. Okay, then I can talk a little bit more. I've sent a copy of my current science article on scientific temper and education separately, and this may help in clarifying issues. Yeah, this is since I have time, I will talk a little bit more. This is a quote by Alfred North Whitehead on religion. It is a very unusual quote. It says, religion is the vision of something which stands beyond, behind, and within the passing flux of immediate things. Something which is real and yet waiting to be realized. Something which is a remote possibility and yet the greatest of present facts. Something that gives meaning to all that passes and yet eludes apprehension. Something whose possession is the final good and yet beyond all reach. Something which is the ultimate ideal and a hopeless quest. It seems to me all this is a nice way of saying we do not know what religion is in a very fundamental sense. And my ideas, of course, are on the other paper which I sent to you. Yeah, and religion, you see, depends really, as Fritjof Capra mentions, on mysticism and some kind of a revelation. And you'll be amazed to know, Mitra asked this question, does religion lead to truth? He also asked the question, will science also lead to truth? Einstein described ecstatic revelations. He has already had one in a article, A Cosmic Religious Feeling. And he believed that values which are crucial for our life are given by people with revelations and not by individual people. Hindus, of course, call this cosmic revelation religious feeling. When Feynman was asked by Fred Hoyle whether he has had any revelation, he said, a few minutes of ecstasy means nothing to me. Whereas Hindus believe, even if it takes several births, it is good to have ecstasy. The first person to bring religion and Wigner together, which unfortunately wasn't successful, was by Wigner. In 1960s, Wigner wrote that the collapse of the wave function takes place in the consciousness of the person. But fortunately or unfortunately, in the 90s, he withdrew this because by that time, people had discovered that decoherence takes place much, much before it goes into the consciousness. So maybe because of that, you can't really invoke this. But as I said, we don't really know much about all these even now. Yeah. Okay. Thank you very much.
Thank you, Professor Sir. So now we have 5 minutes for discussion and feedback, please, from the audience.
May I unshare the file now? Can I stop sharing the file?
Yes, yes, please. Yes, you can raise.
There are no questions, is it?
But still, we have few minutes. Let us wait, sir.
Okay.
Professor Kausal is raising his hand.
Okay, please,
Kausal is
Professor
raising
Kausal,
his hand.
please.
Kaushal is there. Kaushal is raising that.
Yeah,
Kaushal.
please, I have little query. Professor Panchpatkisan, and very good summary of the Professor Mitra's interest on philosophy and science. You see, there are two words used. I still don't understand after so many years. One is Cartesian partisan. Religion and science, they lie in the he calls that Cartesian partisan. Second, what is the contingent plane in the context of work of Holton? Could you please elaborate the meaning of these two?
Pardon? I didn't quite catch the question. Huh?
See, he talks of Cartesian partition
Yeah.
with regard to religion and science. Are they
Yeah.
really Cartesian or they have some overlapping domain? Second thing, he talks of the contingent plane in the context of Holton's work.
Right, that's right.
Are
Quite
they
right.
different
Quite
or
right. Absolutely
same?
right. Yeah.
I have not yet understood this after so many years.
Yeah. You see, the criteria for separating the two things, religion and science, is the scientific method. And he calls this the contingent plane, which is the two-dimensional plane of theory and the verification of experiments. But that is not really very convenient because when you go from science to religion, you're really going from rationality to a whole lot of emotions. Without emotions, religion doesn't make any sense at all, nor does social science make any sense. So I would prefer the method of Ronald Searle, in which he separates the two, one as man-made, rather God-made laws, and other as man-made laws. That probably is a much better one.
Just another query I can have. Nimai Singh, will you
Yes,
permit
please.
me to ask one more?
Yes, we have time.
See this,
No,
with regard to absolute reality. With regard
what would be reality?
Absolute reality. We have subjective reality in the top-down manner, objective reality in a bottom-up approach, right? So absolute reality is a combination of the both, right? So in this respect, what I hear these days in the West, they talk of spirituality but not religion.
Okay.
Yeah. So there's a move in the society. They want to become spiritual but not religious. What are your comments on this observation?
Yeah, no, that is possible. But you see, as Fritjof Capra describes in his book at great length, the whole point about realizing the truth is it gives you a tremendous feeling of Brahmananda. And you see, reality gets totally merged in that. All kinds of reality. There's a whole unity. The unity is much more important than anything else. So Capra uses the fact that quantum mechanics brings much more of unity than earlier science used to do. I don't know how far that is true, but anyway, thank you.
I think we have time. We have finished our budget. So let us thank our professor in Panchapakishan for his good delivery. And these talk require more than 1 hour. we can have
Absolutely.
infuses her again.
Yeah.
Okay, thank you.
Yeah, yeah.
So next, and let's pass to the next speaker.
So I believe we have Professor Mani as the next speaker.
Yes, Professor Harihar Subhamani. Okay. Quantum thermodynamics, a small system, the anionic auto engine, please. Professor.
Yeah, I will share the full slide. Am I audible?
Yes. Yes.
And can you see the slide?
Yes.
Okay. Whenever you tell me to start, I will start.
If everyone would mute, everyone else would mute.
Yes.
Professor Mani, kindly start, please.
Okay, thank you very much. It's a pleasure and a privilege to be invited to such a meeting about Professor A. N. Mitra. I was a student of his. He taught us mathematical methods of physics, and a little later, informally, quantum field theory. He had finished his PhD from Cornell and then come. I had not explicitly written anything for here because I was not absolutely sure of all the details, because I have used my memory, and that's a very long time ago. My memories of him are after Delhi University. I met him in Trieste, and he was looking at the nuclear levels in great detail. I was wondering, who is a mathematical physicist? Why should he spend so much time in working out all the details of nuclear levels? Little later, I realized that he had actually showed the presence of strangeness, which was required to understand the nuclear levels. And I believe he was the first person to show this. It shows the importance of looking at details. Then when I was in IIT Kanpur, I was a candidate for a promotion, and he was in the selection committee. So he did not have any informal exchange. I met him very briefly, and he told me I should continue looking at low energy physics also, which I did to some extent. Now I will proceed with my regular talk, which is on quantum thermodynamics of small systems, the anionic auto engine. This has been done in collaboration with Professor Sridhar and Ramdas. Ramdas was a PhD scholar with Sridhar. Right now, he's a postdoctoral fellow at Math Science. Now I'll go to the next slide. Thermodynamics is an empiric. Shall I proceed? Professor Mitra.
Please.
Okay.
Please
All
proceed.
right.
Please.
Thermodynamics is an empirical and phenomenological description of matter at the macroscopic level. We all know that, where the number of particles in the system is of the order of Avogadro number. It was of academic interest to stretch the thermodynamic line of thinking to small systems in order to probe the limits of applicability of concepts like temperature and entropy. This happened because small systems could be prepared, and in the last few decades, several small systems like single molecules and quantum dots have been studied. They have been studied extensively from the point of thermodynamics. The difference is that this requires to discuss fluctuations in greater detail. We will come to see how to avoid the discussion of fluctuations. When two disparate approaches to physical problems face off, as in the above case, surprises are to be expected. It has happened several times in physics, and there is no exception here. Classical thermodynamics engines like auto engine study and use for over a century convert thermal energy to work. On the other hand, quantum thermodynamic engine affords us an opportunity to harness non-classical, non-thermal sources of energy arising out of quantum statistics to do mechanical work. This is one of the cases where you don't need thermal processing to get mechanical work. So I will do a simple back of the envelope calculation that reveals this. Consider harmonically trapped quantum Bose gas of n particles at 0 temperature. They are in a simple harmonic oscillator. So the total energy of the Bose gas will be h cross omega by 2 times n, because all the particles can occupy the ground state. But if it obeyed Fermi-Dirac statistics, this cannot happen. And Fermi-Dirac, the energy of the Fermi-Dirac is given by the expression. You have to put one particle in each level. We are not assuming any internal degrees of freedom for the fermion. Actually, you can take that. That will not make any difference. So E Fermi is given by this, and the Fermi are occupied. These are the levels occupied, and we get this. So now you see the difference between the two is fermion has higher energy. So ultimately, the difference is so much. Now, this can be extracted provided we can change the system from fermion to boson. This is the basic idea. And some experiments which were reported in Nature actually triggered our thinking. And we proceeded to look at some simpler systems. The energy is non-classical and purely quantum mechanical origin, derived as it is from quantum statistical population distributions, functions of different particles. The main idea of quantum thermodynamics are to identify the non-classical equivalent of thermodynamic concepts, internal energy, heat, and work in a quantum system. Let ρ be a density operator that describes a quantum mechanical system coupled with thermal environment. H lambda be the Hamiltonian for the system. Lambda is a control parameter. And the internal energy is defined as average of H, which is trace of ρh. Where in the weak coupling element, ρ is in the equilibrium state, we will take it to be the Gibbs state, given by the standard Boltzmann formula, which is ρ equal to e to the minus beta h divided by h, where h is the partition function. We all teach this in statistical mechanics all the time. And k beta is nothing but 1 by kbt, and kb is the Boltzmann constant. Again, the Gibbs state entropy is given by minus kb trace rho log rho. Can I go to the next slide, sir?
By all means, Professor Mani, please.
Okay. The change in internal energy can be partitioned into two pieces. dE, d rho h plus rho dh. Now, I will argue that the first term is the change in energy and the second term is the change in the work done. Let us see why. Because notice that entropy changes when rho changes. So if entropy changes, d rho, the first term changes, and dq is related to TdS. So this is what happens here. That's the first term, indicating neither of these. Okay, the first, and then I have put something at the top. We all know what that is. That is path dependent. This is not a state function. And like we do this for work. Now let's look at the next term. The parameter h is varied. So let us think of a particle in a box. Particle in a box has energy h cross squared pi squared by 2 ml squared. Now, if I change L, the parameter of the Hamiltonian changes and work is done. Because I'm changing the length of the system is doing work, or somebody is doing work on the system. So that represents the work done. So this is the first thing which when you do quantum thermodynamics, we do. We associate with trace rho dh with dq and rho dh with dw. I will again wait for a small time and let me know whether this is okay.
Professor Mani, the slide reads well. Please proceed.
Pardon? Can I go to the next slide?
Yeah, sure.
Okay. Now it is straightforward to define quantum analysis of isothermal, isobaric, isochoric, and adiabatic process. There are some subtle points. We'll come to that. hence the various quantum analogues of the classical thermodynamics engine. The Otto engine, for example, consists of 4 strokes, 2 adiabatics and 2 isocores. By definition, adiabatic is one in which no heat transfer takes place between the system and the environment. It corresponds to a change in energy eigenvalues while keeping the populations, hence the von Neumann entropy unchanged. This is a very important point, which is there in thermodynamics of small systems. In isocoric system, where the volume is held constant, the energy levels are fixed. The changes are in the population because in an isocoric process, the temperature can change. When the temperature changes, the Boltzmann function changes. If it is at a higher temperature, higher levels gets populated and so on. So the energy changes. Now, can I go to the next slide or shall I wait?
Please go to the next slide.
Okay. We conclude this brief survey of quantum thermodynamics, and we want to mention a few subtle points in which the classical and quantum mechanics differ. Now, let us look at a classical adiabatic process. This is something which is not a very easy concept to explain when we teach statistical mechanics. Consider a characterized by thermal, of which no heat is exchanged. That is an adiabatic process. When I make a small change on the system, how can I say the system has come to equilibrium? That is not obvious. And this is, if I'm not interacting with the surroundings, somehow the system on its own, it's a very famous problem. And I do not know any detailed mathematics of it, but there is a time scale. The time scale is in which the system comes to an equilibrium. And this time scale of coming to equilibrium should be less than the other time scale of when it is expanding. Thus, the time scale of the adiabat should be less than the decoherence time scale. Can I go to the next? Because this is a very important point.
Yes, please. Kindly go to the next slide.
Okay. Unlike classical thermodynamics, we have systems which are reversible and are in instantaneous equilibrium throughout. In quantum thermodynamic engine, we have the following problem. We all know quantum adiabatic theorem. In quantum adiabatic theorem, the system should move so slowly that if you want it to remain in the same level, the time scale should be such that it should be more than the time scale associated with the energy difference in the various levels. Of course, H cross is involved in making it unit. This is one of the important points in understanding. So a system may be an adiabatic classically, but it need not be an adiabatic quantum mechanically. Because when I am making the system move slowly, but fast compared to the energy level difference, the quantum system will automatically not satisfy the quantum adiabatic theorem. Okay. Now I will go to quantum Otto engine based on qubits. 3-level systems, harmonic oscillator, statistical ions have been extensively studied. In this paper, we study the quantum Otto engine with a working medium with a very small number of one-dimensional anions. We will talk about what is anions. Anions, particles which are intrinsically have quantum statistics, which can smoothly interpolate between the bosonic and fermionic statistics. This has been going on for quite some time. It came from statistical mechanics, where fractionally quantum Hall effects were observed when anions were discovered. I think Jain was an important contributor to this. Now, how do we do this? How do we change the statistics from fermion to boson and vice versa? Here is the main idea. I have some kind of a flux tube. B is a flux tube. And I have a charged particle which is going around. If I change when a particle goes around, it picks up a phase of e to the power of I loop of the integral A dot dl. A dot dl is nothing but the magnetic flux passing through this surface. I will repeat it. I have a magnetic field confined to this in this direction. When the magnetic field is in this direction, I have a charged particle which is moving in a ring. It is constrained to move in a ring. Now, if when it comes back here, if it were a boson, it should have the same phase. If it were a fermion, it should have the opposite phase. But in general, it will have some arbitrary phase depending upon the flux that is passing through this. So now I have a control of how to change the statistic from boson to fermions. Here it is. Magnetic flux is B into A. A is the area of the loop here, because we assume there are no magnetic flux here. Since this is infinitely long, the magnetic field will go out to infinity. Although it doesn't make sense about statistics of individual particles, it may be considered as a toy model of an anion. Again, this is a question which was raised right in the beginning when quantum thermodynamics of small systems were formed. The answer to it was you give several Gibbs examples and work with averages from the Gibbs ensemble rather than the other ensemble with a large number of particles. So that was the answer for that question. So let me repeat here. Although it doesn't make sense to talk about statistical energy, this may be considered as a toy model of an anion on a ring. To verify this, all we have to do is consider two particles on a ring and exchange their positions. The vector potential has only A phi by 2 pi r. The Hamiltonian for a charged particle, we all know that 1 by 2 pi m. This is just the standard gauge transformation we make and write it down, which is equal to, I write P phi as its cross squared so much. The normalized energy levels are given by this. N is an integer with eigenvalues. So now notice this is and E is nothing but where alpha is the value coming from given by the flux. This is a standard thing which we also use in superconductivity and so on. I will now go to the next slide. Okay, here is the diagram. I have entropy and the temperature. These two are adiabatic, entropy is constant. And these are isomagnetic. Instead of isochoric, we have written it as isomagnetic. Magnetic field is constant. The four strokes constitute are, the first step, we move from A to B. The system changes its temperature from T1 to TH. This is achieved by bringing it to contact with an infinite baths, several baths at each infinite temperature, T1 to T2 plus so on, and go on till it comes to TH. This is a standard procedure. You make infinite bath transformation to reach there, so that we can consider that in thermal equilibrium in the entire process, and we can apply the equations of thermodynamics. NDT, a number of steps, and we get a reversal pass. This is because the entropy change in the reservoir and the system is zero at this stage. Similar argument holds from C to D. So I go from here to here, here to here. A to B and C to D are isomagnetic process. So thus called because no work is done along these paths. Recall that changes in energy levels are affected by changes in magnetic field. The strength of the magnetic field A to B chosen to be BH corresponds to the energy. EHN is given by this expression, where alpha H is equal to BA squared BH. Similarly, from C to D, the energy levels are here to here. Let me just tell you, the first one was the energy level change from A to B, and the second one was from C to D. Now it is very easy to calculate. Alternatively, we can keep the magnetic field constant and change the radius of the ring. If I change the radius of the ring, it will automatically change. This is another way of doing the same thing. So we have two different methods. The experimenters can choose whichever is convenient to them. Now notice, if the radius A2 is greater than A1, the energy level decreases. Since the occupation probabilities remain the same in an adiabatic process, work is done as we go to the system as we go. So if I increase the size of the ring, there is more work done. Where I decrease it, the work done is the opposite. Note that only state B and D are in thermal equilibrium. B and D are in thermal equilibrium. These two states are not in thermal equilibrium. The efficiency of the quantum Otto engine is given by WQOT is equal to this 1 minus, you can calculate that expression clearly, which is, I substitute various values for PA and PB. Notice these B and C are equal because they are isentropic. Same way, these are entropic. So I can write it in this form. And one can simplify this, and I will not spend some time to do that. The sums appearing that can be calculated in a straightforward manner and can be given an analytic expression in terms of some things which these are gamma functions of some general functions which I will not describe here, but they are all doable. There is no major problem. Jacobi theta function in terms of these. There are several other things which one can do to convert bosons to fermions. We have written one more in the paper, one more paper, we are about to write it, and that's where it is. And I thank all of you for the attention and the patience. And so if you people have any questions, I'll be more than happy to try to answer. Not that I know everything associated with this field, but I enjoy working in this area. Thank you.
Thank you, sir. We have about 10 minutes. We have enough time for interaction, feedback, as well as any comment. Thank you. I open to the audience.
Sir, can you please more elaborate about the anionic word?
Yes. You see, in bosons, when I have not drawn the diagram, you can do that. But bosons, if I interchange two particles, the sign of the wave function doesn't change. But with fermions, it changes sign. If I do the same thing here, let me go to the diagram. Here, supposing I keep one more particle here, then I interchange. What does that interchange mean? This goes here and that comes from there to here. So the total change is essentially e to the power of I, the flux passing through this. Please realize this is one goes here, the other comes here. So the entire change is the full circle. So, but e to the power I a dot phi need not be equal to 0 or phi. Need not be an integral multiple of 2 pi or an integral multiple of pi. So that is why when I interchange these two particles, they don't have a property of fermion or boson. I hope I have clarified it. It's not. If not, I will repeat it in a slightly different way.
Yeah, thank you, sir. Thank you.
Fine. Yes, Haridas.
First question, why Otto cycle? There are many cycles in thermodynamics. Why did you pick the Otto engine?
Very good question, Haridas. With Carnot engine, it will not work very well because Carnot engine is independent of the system, as you have pointed out in your book very clearly. And secondly, we can use diesel engine. The calculations are more messy.
Second question, you identify the d rho term with d bar q, but d rho is an exact differential. D bar q is not. So
which slide are you talking about?
In your very first identification of the first law for the quantum case.
That is so only if it is a reversible process.
Whether it is reversible or not, d rho is an exact differential.
Oh, d rho, of course, is exact. That's correct.
But you identified with d bar q, which is not an exact differential.
That is correct. That is a exact differential when the system is in equilibrium. It is TDS.
Okay. Thank you.
Oh, you're welcome. We spent a lot of time trying to look at other engines, and ultimately we resolved. Now, I want to make one remark about Haridas's book. That's the first place I learned that Carnot did not use the theory of heat that we use today. He had used some other liquid theory and so on, yet got to the result.
So is there any more question? Otherwise, we have saved 5 minutes. We can pass to the other speaker so that he may gain 5 minutes more.
Can I stop sharing?
Yeah.
Yes, please.
Done.
So we have Professor Haridas as the next speaker.
Yeah, I'm ready.
Professor Nima, you're muted.
So, Professor N.D. Haridas, QCD string and effective string theory. Please start, sir. Please.
Thank you. Where are my slides?
Okay, just give us a second. Sorry.
I don't see my slides.
Yeah, just give us a second, please. Yeah.
Yeah.
Just a second.
Anyway, in the meantime, it's a great honor and privilege to be part of this meeting to remember our dear teacher, Professor Mitra. I was a student both in my honors and in MSc days, and afterwards we were constantly in touch with each other. And as I will explain in my talk, he is the one who opened my eyes to the world of elementary particles, and in particular, the quark model. So is this full screen? It doesn't seem to be. Alok?
It is not a full screen, but still we can see.
Let me try. Sorry.
Okay, so I'm going to be talking about the topic QCD strings and effective string theories. This summarizes a body of work, both analytical and numerical, that I have done with several of my collaborators. And this will be a summary. And in a way, it's a very apt tribute to Professor Mitra, as he is the one who introduced me to the quark model. So my academic journey began with the quark model, and more or less, the end point of my academic journey, formally speaking, also had to do with quark theories. Next slide, please. So, tribute to Professor Mitra. He really opened our eyes to the magical world of elementary particles. To say that is only an understatement, but by the end of this symposium, we will all know the true import of his impact on all of us. Next slide, please. So this is the stage where it all happened. The wonderful days of our honors and MSc in Delhi University, all the lectures were here. Professor Mitra's magical lectures on mathematical physics also started our interaction at what I would call this the unforgettable stage for me. Next slide, please. So, quarks, Mitra, and me. The quark model was proposed independently by Gell-Mann and Zweig in 1964. For my MSc thesis in 66, 2 years after the quark model was founded, Mitra suggested working on the meson and baryon decays in the quark model. He was clearly among the few worldwide that took the quark model seriously right from its inception. As we all know, not everybody took this model very seriously. The year after that, in 67, I went to UC Santa Barbara, barely 100 kilometers from Caltech, where the quark model was born. And incidentally, while writing my recent book, I discovered a Mitra Santa Barbara connection, which was the paper by Mitra, Gillespie, Bob Sugar, and Nargis in 65 on 4-particle scattering. But nobody took the quark model seriously in Santa Barbara, for that matter, in the whole of the West Coast. Feynman even made fun of them, calling it the quack model. So that was the situation. Next slide, please. Now let me go a little bit deeper into the quark model. The quark model was an outgrowth from the so-called Sakata model, eightfold way, SU3, etc. Incidentally, the spectacular prediction of the omega minus owes it to the eightfold way and not to the quark model, as is often or sometimes claimed erroneously. The Sakata model needed anti-baryons even to build baryons, and to avoid this, Gell-Mann and Zweig introduced fractional baryon number and fractional electric charge for the quarks. Almost immediately, the quark model was seen to suffer from the so-called statistics problem. In 65, a year later, Hahn and Nambu came up with an alternate quark model, which not only proposed ways of solving the statistics problem, they did not call it color, but also paved the way for quark dynamics through what is now known as the gauging. Next slide, please. In hindsight, it was a monumental opportunity missed that we did not study the Hahn-Nambu paper more closely and focus more on the Gell-Mann-Zweig model. And this regret is not just mine. No less than Gell-Mann himself had this to say. He said, if I had read Nambu's paper, it would have set me ahead by several years. And in another context, he said, Nambu then invented what amounted to QCD, or the beginning of QCD. Next slide, please. So now I'll briefly talk about the birth of what we call the quantum chromodynamics. The attractive feature of the Hahn-Nambu model was the electric charges were integral, unlike the fractional charges of the Gell-Mann-Zweig quarks. But a heavy price to pay for this was that there was an unavoidable mixing of flavor with color. It took almost a decade for the correct identification of color in the Gell-Mann-Zweig quark model. But when they did identify, it was a supremely elegant solution and completely avoided any color flavor mixing, leading to quark dynamic, color dynamics, which is completely flavor blind. And that has played a major role in the development of QCD. It was identified by Gell-Mann and Fitch as the fundamental representation of a new SU3 group called the color group. Quark dynamics was realized through the Yang-Mills theory of the color group. Rather ironically, even to this day, there are no acid tests to distinguish between the integral charge Hahn-Nambu model and fractional charge Gell-Mann-Zweig theories. This was shown by extensive works of G. Rajasekhar and his collaborators. Next slide, please. Not everyone subscribed to the quark model for a variety of reasons. Even quantum field theory itself was discredited on the West Coast, where I went to do my PhD. And, instead, it was the S-matrix approach pioneered by Heisenberg that was very strongly championed. After a decade-long, rather impressive line of developments like dispersion theory, dual resonance models, the relativistic strings idea was proposed in 1970 by my dear friend Holger Nielsen, Nambu, and Susskind to explain many features of strongly interacting particles called hadrons that could not at that point be explained by any relativistic quantum field theory. But this idea also ran into several difficulties as it required space-time dimensions to be 26, tachyons, etc., and was abandoned by many in favor of the Gell-Mann-Fritsch quantum chromodynamics. The punchline of our work is the emergence of strings within QCD itself. So in a rather remarkable way, these two divergent paths are now brought together. Next slide. The major unsolved problem for QCD is that of quark confinement. Simply stated, no free quarks had been observed even during very energetic collisions between hadrons. That would not be so if hadrons were bound states in the traditional sense of a quantum field theory. What should have been a theoretical embarrassment was turned into a virtue with the proposal that quarks are permanently confined. And this is the principle of permanent quark confinement. But the challenge was, it was far from clear if any quantum field theory, leave alone QCD, could ever possess such a property of permanent quark confinement. Next slide, please. A breakthrough in this regard was the idea of the dual superconductor. To appreciate this, imagine a magnetic monopole, anti-monopole pair. Magnetic monopoles don't occur in nature, but a Gedanken experiment with monopoles and anti-monopoles is always possible, and immerse them in a superconductor. The superconductor would tend to expel the magnetic flux everywhere, but flux conservation will not allow flux to be expelled everywhere. This is like the Hindi movie situation where Ajit says, "Isko liquid oxygen में डाल दो, liquid इसको जीना नहीं देगा, और oxygen इसको मरना नहीं देगा," right? So here, superconductivity and flux conservations would lead to this situation. So what's the resolution? The resolution is, in a superconducting ground state, a very thin flux tube would be developed between the monopole and the monopole, and flux conservation would lead to constant energy per unit length. So if the more you want to separate the monopole, anti-monopole, more energy linearly rising with separation has to be supplied to render them free. In other words, the thin flux tube would confine forever a magnetic monopole, anti-monopole pair. So, at least in principle, it was settled that permanent quark confinement is indeed a possibility, but for that, the ground state of QCD would have to be a dual superconductor. Why dual? Because it is not the magnetic charge that has to be confined, but the color electric charge. So we have to switch electric and magnetic attributes. So the QCD vacuum has to behave like a dual superconductor. We are now only passing the buck. Now the challenge is to show that QCD vacuum indeed does behave like that. Next slide. Analytically, this has been a big challenge. Though wonderful ideas have been put forward, we are far from solving this confinement problem analytically. And there is, in fact, $1 million prize by the Clay Mathematics Institute for anybody that will give such a proof, but mathematicians will never accept our proof, and we physicists should not waste our time trying to win this $1 million prize. But numerical studies of QCD or lattice, that has opened the floodgates literally. Now on the lattice, flux tubes can be investigated by so-called Wilson loops, which is what I've shown on the right-hand side, which is just a square or rather a rectangular loop, or what are called Polyakov loop correlators, as shown on the left. The central object of interest is the static quark antiquark potential. I'm only dealing with pure gauge theory at the moment. Then the expectation value of the Wilson loop would go as exponential of minus t times the quark potential. Likewise, the Polyakov loop correlator will also have the same. So by studying this for large enough R, you can literally measure the static quark antiquark potential, and from there see whether there is indeed a confining force or potential between them. Next slide, please. So for large separations, we can simply expand the potential. The leading term is linear, then the subleading powers like 1 over r, 1 over r squared, 1 over r cubed. Sigma equal to 0 signals linear confinement. You must remember, confinement doesn't require the potential to grow linearly. As long as it grows as any positive power of r, it will be confining. But when it grows linearly, it will lead to linear confinement. On rather general grounds, which I cannot go into, called the open string, closed string duality, you can show, or Lucier and Weiss showed, that the coefficient B is exactly 0. A has the value d minus 2 over 24 pi, irrespective of the gauge group. It's completely universal, depends only on the dimension of space-time, and it is called the Lucier term. It should not be confused with the Coulomb potential, even though it goes as 1 over r, because the realm of validity for this is large distances, unlike the Coulomb potential, which dominates at short distance. The first term is so big that it's very clumsy to study V of r itself, as the first term will dominate everything else. So it is better to introduce a convenient dimensionless quantity, which is basically the scaled second derivative of the potential. Then for the above, it will look like A plus BC over R squared. So for very large distances, the value of this C would be the Lucier term, and then one can see whether the subsequent corrections or not. Next slide, please. There is overwhelming lattice evidence for linear confinement, which manifests as the area law for large Wilson loops. But in addition, rather impressively, even the entire profile of the flux tube has been very accurately studied. And here I show a beautiful result due to Gunnar Bali, etc. Here is the flux tube between a quark and antiquark. And at both the quark and antiquark ends, you see a Coulomb-like peak signifying perturbative quantum chromodynamics, where instead of 1 photon, you have 8 self-interacting gluons, and those peaks can be completely captured by analytical perturbative QCD calculations. But in between, you see a beautiful flux tube that has developed between the quark and the antiquark. Next slide, please.
So you have 25 minutes gone. Okay.
How much more time do I have?
Yeah, please take 5 minutes only.
Okay.
For question.
Anyway, the slot is 10 to 10:30. Thank you. So a breakthrough in these studies came from an amazing algorithm by Lucier and Weiss called multilevel. With this, the A term could be studied to 15% accuracy, and they unfortunately stopped short of exploring the most critical region. Next slide, please. So in 2004, as part of the 10th plan, as well as the objectives of an alliance called Indian Lattice Gate Theories, which I lightly call the LGT Gatabandhan, I built a teraflop linear cluster called Kabru. It was in the top 500 supercomputers of the world twice in a row. I was looking for a worthy problem to put Kabru to work. Next slide,
Sorry,
please.
sir. You're right. You're right. I am mistaken. You have enough time. Okay. 15 minutes.
No problem.
No problem.
I'm very conscientious about time. Next slide, please. Next slide. Yeah. So I undertook these studies with Pushan Majumdar. Pushan passed away at a very young age in 2020, who at that time had become a world expert on the Lucier-Weiss multilevel and had applied it to a number of interesting and fundamental problems. We decided to do a very thorough study of flux tubes in 3 and 4 dimensions with SU2 and SU3. Utilizing all the design features of Kabru, we could handle much larger lattices and, more importantly, push to larger QQ separations, which turned out to be a game changer. Next slide. So here are the numerical studies, results of the numerical studies. On the left side, you have the 3-dimensional SU2, and on the right side, you have 4-dimensional SU3. You know, what you can see is at the short distance end, there is complete agreement with perturbative QCD, both in 3 and 4 dimensions. And at the right-hand side, for very large distances, there is an impressive convergence towards the string-like potential. So in one slide, it achieves the main message of QCD, that it achieves a beautiful interpolation between asymptotic freedom at short distances to confining string-like behavior at large distance. Next slide, please. Now, the exact potential or the ground state energy of bosonic string theories is the so-called Orvis potential, and you can expand it, and our measured values reproduce this very well already when the quark-antiquark separation was 1 Fermi. So what our studies indicated was that to a high degree, flux tubes actually behave like the fundamental bosonic strings. But bosonic strings are consistent only in 26 dimensions, but QCD is a consistent theory in 3 and 4 dimensions. So how could I use a formula meant for 26 dimensions and formally plug D equal to 3 and 4 and still see this spectacular agreement? A numerological accident? Extremely unlikely. Next slide. So here, Polchinski and Strominger came up with an idea. They were motivated by Polyakov, who showed how to formulate string theory even in 3 and 4 dimensions. But as fundamental string theories, they had a large number of problems. So Polchinski-Strominger idea was to take the message from Polyakov theory that when you go to subcritical dimensions, you have to introduce new degrees of freedom, and therefore they took the string theory action and added to it a non-polynomial term of that type. Next slide, please. Such string theories become consistent in all dimensions. This is a technical point which you have to look at the literature. But the action itself is sick for many configurations. but remains sensible for small fluctuations about a straight confining string configuration. So the interpretation is use the Polchinski-Strominger action as an effective theory. It's also a higher time derivative theory, but it has exactly the same local invariances as string theories. Next slide, please. So we obtained various results, which Peter Matlock analytically showed in 2006 that to order r to the minus 3, the spectrum of these theories is the same as that of bosonic string theories, so vindicating our numerical studies. With Peter Matlock, I also developed a covariant calculus with which effective string theories can be constructed to arbitrary order. With Peter and my ex-student Yashas, we proved a number of results which are beyond the scope of this talk. Next slide, please. So I will end by giving you an effective bibliography. And this is my recent book, String to String, which covers all these topics, all the technical details, vast bibliography, and the theoretical requirements like non-perturbative quantum field theories, dispersion theory, S-matrix theory, birth of string theory, all in one book. By the way, I'm not hinting that you buy my book. The salient results are also summarized in this archive article, Effective String Theories of Yang-Mills Flux Tubes, and that is the archive reference. Thank you very much. And thanks once again for this opportunity. And I'll be happy to answer any questions that may arise.
So thank you, sir. We have about 8 minutes, so we can have a lot of discussion, please.
Should I unshare the file? Can I stop sharing, or should we keep it up?
Can I ask a question to Professor Haridas?
Yes, please.
Tell
Hello?
me. Yeah.
Haridas.
Yeah.
You mentioned about you're familiar with his work on strangeness, right? He showed that I think it's deuteron, where he found that you need strangeness to understand the spin of the levels. Is that correct?
No, this dual string model I've not really studied very much, so I'm afraid I can't answer your question.
I see. Do you know anybody else here, Professor Mitra, who might? I'm curious. No, I've forgotten this.
What exactly is the question? Maybe I can rephrase it in a different way.
You want me to rephrase the question?
You can ask your question. I'll see if I can rephrase it in my language.
Okay. Professor A.N. Mitra had discovered the presence of strangeness by studying the nuclear energy levels. If I remember right, it was deuteron or triton. I don't know whether it is H2 or H3. Do any one of you remember the argument?
Okay. No, not me.
All right. I will look up and I think I'll be able to find out.
Sure. I will also do that.
Okay, good.
Might I ask a question, please?
Yeah.
Sir, can you little bit more elaborate about the effective string theory? What does the effective means here?
I didn't hear you very well. Perhaps you could type your question on the chat and I can read it. I'm a bit hard of hearing in spite of my hearing aid.
I'm asking about the meaning of effective string theory.
The meaning of the effective string theory.
Sorry?
The meaning of the effective string theory.
Yeah.
That is the question.
What about the effective string theory?
Meaning, yes.
Yes.
Exactly.
It's exactly like effective field theories. For example, long before QCD was solved, we had an effective chiral field theory of pion and pion-nucleon interactions, the spirit is exactly the same. In superconductivity, the Ginzburg-Landau effective theory was successful in explaining many things long before the BCS theory came about. So effective string theories will capture the symmetry aspects of strings, but not very detailed requirements like the action be well behaved, etc., etc. So they will be valid in a limited domain of string configurations, but not for all string configurations as a fundamental string theory would do.
Okay, thank you, sir.
Professor Nimai, may I ask a question, please?
Please continue, please.
So, Professor Haridas, I was just curious. This Polchinski-Schrodinger's action that you showed, is it ghost-free?
Yeah. Well, no, it is both closed. I mean, the one I wrote was for closed strings, but there is an open string version of the Polchinski-Schrodinger's action also. So, in fact, there is a notion of an open closed string duality even for these effective string theories. So closed strings is not a restriction.
No, what I'm asking is it ghost-free?
Both string.
Ghost, because it has higher order time derivative terms?
No, of course not. Because, you know, it is ghost-free in certain domains, in the sense that the effective strings also do not excite any negative norm states. But if you go to very short distances and apply this theory, you will have all the sicknesses of string theories, bosonic string theories.
Right, thanks.
Any more question, please? So otherwise, I was told that Professor Mitra also had some work before the event, before color hypothesis, that we need some sort of extra degrees of freedom. He used to call nodes and anti-node. From his calculation, he saw that there is a need for extra degrees of freedom in old quark model. Later on, it was called color. So I heard like this, but I don't know much in detail because it was not my work.
Well, I have also heard this, but I have used color in a very precise sense, as used by Gelman, Fritsch on one side, and Hahn and Nambu on the other. And I am not aware of any work of Mitra which identified color in such a deeper level, but I could be mistaken.
So if there is no further question, let us thank Professor N. Haridas for his extremely useful talk. Thank you, sir. Thank you. So I pass to the next speaker, Professor Dayananda Parasar.
Thank you very much.
Formulation of the Dirac equation in curved space. Professor Parasar.
So actually, Professor Parashar today morning had shared the video of his presentation. So let me try to share that. Share sound. Thank you. Optimize for video sharing. Yeah.
Good morning to all, and my greetings to everybody.
It may be bigger.
The topic of my talk today pertains to Dirac equation in curved space-time. Actually, this is based on my 3 research papers that I wrote in early 90s, that means 1990 and 91 and 92. And of course, there have been lots of developments subsequently. So I'll try to cover as much as possible within the limitation of the space that is allotted to me. And this quick review is presented in as a tribute to the memory of my revered teacher, Professor N. Mitra, who has been a constant source of inspiration for me all through my academic career. And I will be speaking mostly about some of the salient features, not going into the details. But before I do that, I would like to have a few reminiscences of Professor Mitra, which date back to 1991 to start with. It was in 1961, as a first-year student. We were having a class in room number 2, the lecture hall number 2. The class was on mathematical physics, and then suddenly professor comes from the small gate of the office and completely unnoticed. The class did not believe. It was a total astonishment on the part of the students. They could not really recognize that that young man, looking more boyish than a teacher, would really be a teacher indeed. So, but that he was. So that is how we got started with him. That was the very first class that we had in the university after passing out from the school. So he inspired the students by giving anecdotes of brilliant scientists like Fourier and Laplace, and always insisted that people should try to look for beauty in all mathematical formulations that are important for carrying out research in or advancement of theoretical physics particularly. Now, when I was in MSc, he gave a course on QED, quantum electrodynamics, and everybody was enamored of his lectures because he taught long derivations in the class without any notes, without getting aided by any notes. So the class was really very enthused about his, not only about his physical insight into the theory, but also about the language, the fluency and the brilliance that he exuded. So that was a great source of inspiration to carry out some of those ideas further if ever somebody wanted to take research as a career. Then after I graduated and did my master's and joined college as a lecturer, I wanted to work with him for my PhD. And I talked to him and he immediately said, yes, why not? Then in 1969, he put me into the field of quarks, which were hypothesized just around that time by Gell-Mann and others. So he asked me to try quarks of spin 3/2, because nobody knew at that time whether the quarks carry a spin half or they carry the quarks carry spin 3/2. So he asked me to find out a few static properties, which I did. It took me almost 3 months, and with long calculations of this higher spin quarks that and kind of para quarks, as they were called, because of certain difficulties which were associated with the satisfaction of the Pauli's exclusion principle. So we tried to do this, and when I showed my draft to Professor Mitra, he said, yes, this is a brilliant idea, and you try to get it published. So I sent it for publication, and it was accepted within 2 weeks at Novo Cimento. So that was my first independent paper on his advice, and it really fueled my zeal to go further into learning the subject. So after graduating, after writing this paper, I was offered a fellowship to work for my PhD at the University of Hawaii. And during those days, that was, I think, in 1972, that Professor Mitra was invited by the Department of High Energy Theory. And he was requested to give a talk on quark physics. So particularly people were interested as to how he got the idea of quark color symmetry and why color was really necessary. So he gave a wonderful talk which was really applauded by the physics community and also by those who were not practicing physicists. So that was the greatness of Professor Mitra. So then, of course, when he had a tough day at the university with so many engagements, I requested him if he would really like to visit the city and see some of the interesting things that city of Honolulu would offer. So I took him to Waikiki Beach, much against his initial reluctance, just to take him around and be acquainted with how things are shaping up there. So after seeing the life at that beach, he remarked, though briefly, how could anybody do any serious physics in the midst of all those diversions? So these were some of the things that happened at that time. Okay. And then during the same time when I was busy doing my research, there was a conference in Hawaii in 1972, and there Professor Richard Feynman was also supposed to give a series of talks there. His topic of the discussion was pertaining to the quarks, quark partons, and the associated distributions. And our group was also interested in doing some salient features of quark distributions, which we did and published 2 or 3 papers at that time. So during a discussion, when my professor advisor, PhD advisor, actually introduced me to him, he inquired where I was from. So when I told him I was from the University of Delhi, then he immediately said, "Wow, do you know Professor Mitra there?" I said, "Yes, I do. He has been my teacher, and he had some excellent words to say about Professor Mitra, and he told me that he has sharp intellect and mathematical acumen." So that was the kind of respect that my teacher commanded. Then, after my PhD, I was invited by Professor J.D. Bjorken at Stanford in 1974, and I was invited to give a talk at Stanford, particularly on quark distribution functions. Bjorken asked me if I could carry some of his reprints, that means BJ's reprints, with me to Delhi to show it to Professor Mitra and seek his suggestions and observations on those papers. Such was the recognition and reputation of Professor Mitra. Okay, now some preliminary ideas about why we really chose to learn about the Dirac equation, which was really extremely important. Ever since it was developed, it was in the early days of quantum mechanics. Actually, Dirac combined quantum mechanics, the original non-relativistic quantum mechanics, with relativity theory, and he also developed the Dirac equation, which also just one minute. Linearized the Hamiltonian through some prescription which were not ordinary, to say the least, because the momentum and the mass and energy, that relation gives the positive as well as the negative energy for free particles. So negative energy was considered to be a very difficult situation to account for, and since the momentum was not bounded, the largeness of the energy in the negative domain kept on increasing. So there was hardly any ground state. So there was eventually a collapse of the system, which was totally unstable. So how can that situation be resolved? So the ordinary interpretation of a wave function was to be modified, that the wave function should be replaced by the corresponding quantum field. Now, Hamiltonian sphere is given in terms of p square plus m square, where h is I ddt and p is equal to minus I del. So these were the Schrodinger operators which were already there, and just to linearize the Hamiltonian, it was not possible through the introduction of numbers or even functions. So Dirac proposed that the Hamiltonian could be written in terms of certain matrices. So he linearized it by writing H is equal to gamma 0, gamma dot p plus m. That was a very bold assertion, where gamma 0 and gamma are Hermitian traceless constant matrices, which would satisfy this relation. Gamma nu is given in terms of 2 g mu nu going all the way from 0 to 3. And then when this is substituted back into the relation, we obtain the Dirac equation as I gamma mu del mu minus m operating on psi x, some function psi x, which should give you 0. So this is the celebrated Dirac equation. And in terms of the Feynman / notation, this can be cast in the form that it has been done here, the last line. Okay. Now, since gamma matrices are not unique, the solutions of the equation psi x will also not be unique, but they can be related through some unitary transformations. Both positive and negative energies, energy eigenvalues, will also occur in a single particle interpretation of Dirac equation. So these are some of this is how the solutions would look like. And the positive energy solutions posed absolutely no problem. Particle momentum P and so EP can be positive. So positive energies have no difficulties in explaining. So negative energy solutions created another problem, because for free particles, how can the negative energy be meaningful? So Feynman actually came in and he gave an interpretation that negative energy particles are viewed as positive energy antiparticles moving backward in time and with momentum in the opposite direction. That was a remarkable interpretation given by Feynman of these negative energies that were there. So this is how. Then, of course, the people were interested as to how the electron can also be, also feel the curvature of space-time. That means how it can encompass the gravitational interactions in a very simplistic way. So the Dirac equation can be remodeled through the introduction of these gamma mu, capital gamma mu spin functions. Also, the gamma mu, the ordinary matrices, gamma matrices, they are now space dependent. They depend on X, just as capital gamma depends on X. So do these gamma mu's, small gamma mu's. So these are the curved space matrices, gamma mu and capital gamma mu. They are the spin connections, which can be evaluated in terms of affine connections for the Robertson-Walker metric. So this is how the next equation number 2, gives you the structure of the Robertson-Walker metric. And here, A, the little a of t, this is some unknown function of the cosmic standard time, and it can be cast into a form as it has been shown here. K has the value 0 plus minus 1 in certain units of time. And carrying out this process, one can incorporate the effect of curvature of space, which means it has ramifications in terms of the gravitational field. So carrying this whole stuff out, you can always obtain this relation, which I have written as equation 15 with all these bulk equations and so on. This is the Dirac equation for the full Robertson-Walker metric. So it contains the effect of curvature, and if the curvature is allowed to vanish, it will fall back to the ordinary Dirac equation. So we generally parameterize the parameter A in terms of different chosen models. One of them is the one that is considered by Schrodinger, A equal A0t, which is proportional to t, it's linear in t. And another one, which is radiation dominated universe. So A is given as A0 square root of t. And then, of course, there is a third inflationary universe model, which is given there. Okay. So when the xi term or the k term as such, since it corresponds to the effect of curvature, and when this goes to 0, our equation falls back to the exactly the same equation which was obtained by Baruth and Duru in 1987. So these effects cannot be really neglected when the curvatures are extremely large. That means the effect of gravitational field is more meaningful in those circumstances. So, but in doing so, simplicity has been sacrificed for the purpose of rigor and generality. So this is precisely what we have done. And there have been several other attempts by other people. For example, Professor S. Chandrasekhar in 1992 found some solutions to Dirac equation in Kerr space-times. The geometry was different from what we have taken. And then much later, in the year 1995, Baruth and Singh also obtained generalized solutions under simplifying assumptions. So nowhere has it been possible to find the exact solution so far. Suko and Unal, as recently as 2007, investigated solutions to the Dirac equation in 2+1 curved cosmological spacetimes, and because they are compatible with a universe where the contraction takes place from an infinite size to a non-vanishing minimum radius, not zero, non-vanishing minimum radius, and then expanding again. So this is how the solutions have been obtained. Okay. All right. All right. Now, I would try to finish this by closing comments. For instance, the linearizing the Hamiltonian through redefinition was found to be intellectually very discomforting in the beginning, as it was undoubtedly a new and bold departure from the routine. And this is precisely what happens with most of these radical ideas. However, this is not surprising, as most of these ideas are generally greeted with suspicion and in many cases with disdain, till they are comprehensively refuted by the experimental evidence. Dirac's theory, based on these unconventional premises, proved to be a game changer, however, as everybody knows now, when the predictions were successfully tested against experimental findings. Now, Dirac was a very different kind of a personality as a scientist, as a person. So he was described as a taciturn genius whose whose volubility was described by his colleagues at Cambridge University, though unwittingly, in terms of a unit which they coined as Dirac, representing one word per hour. That was after a lot of insistence on the part of Dirac, because earlier his friends and colleagues had defined that unit as 1 word per year rather than per hour. So that was an agreed kind of volubility that was ascribed to him. He would invariably spend quite a time in quiet contemplation, and yet his brilliance dazzled all throughout the theoretical landscape and contributed to the advancement of theoretical physics. These are some of the papers that I have listed. My papers are there, and all these relevant papers, but there is a huge list which, if somebody is interested, can go through. Now, before I end, I must pay deep prostrations at the feet of my guru, my revered, most honorable teacher, Professor Mitra. This is a picture which was taken in 1972 at the Honolulu airport, where I had gone there to see him off. And on the right is my Indian professor Sandeep Akwasa, and Professor Mitra is there in the hat talking to the gentleman at the counter. This is a picture which I was fortunate to have with him there. And here is another one where this is probably at one of the stores named Long's Drugs, where he wanted to buy some small doll for his daughter Gargi, and that's how he is also seen here. After all, he's not interested. He never was interested in shopping, but we took him there just for the sake of it. So that's how I conclude my presentation, and I am eternally grateful to my teacher, And this lecture and these reminiscences go a long way in expressing my deep feelings about a great man that I was lucky to have as a teacher. Thank you very much indeed.
Thank you, Professor Prasar. So we have exactly 5 minutes for discussion and feedback. Please continue, please, from the audience. Please, question from the audience. So it appears that there is no question. Then let us have 5 minutes and for the next speaker.
Sir, I have a question.
Oh, please. Then.
Sir, it is a Dirac equation in a curved space-time. So I don't know, as I know, to write down Dirac equation in a curved space-time, we generally use some another notation, means some Beerbines. So I just want to ask whether I am right or wrong. Can someone?
You are from physics or mathematics?
Yeah, I am from physics. My question is just write down to Dirac equation in a curved space-time. As I know, we use Beerbines or yes. So Professor Kulsister may be giving the answer.
Or any Professor Purser may answer the question.
I know very little about it, but I think it's the correct description that I know. It is primarily from beginner, as I read it on some supergravity papers. And so in the Minkowski space, your gamma matrices are fixed; they are constant. And of course, they obey the usual Clifford algebra and so on. And they continue to obey the same Clifford algebra. However, for writing or studying Dirac equation in curved space-time, you have to promote these gamma matrices to the field, no longer constants, no longer fixed, but they become functions. They become fields, just like any other field. Okay, so they are functions of x mu. And Clifford algebra remains the same, and so on. This is the basic point that I would convey to you is, as per my understanding, the gamma matrices have to be promoted to fields. Yes. So and satisfying the usual Clifford algebra.
Okay, sir. Thanks.
Can I
Professor
also?
Kaushal has,
Yeah, actually, when you do the abstraction aspect, either covariant formulation or very abstract formulation, these Beerbines they appear. But here, the curvature is introduced by introducing the x dependence in the metric itself, that kind of thing. So I think somewhat easier and different style from the formulation of GTR.
Thank you, sir.
One more question, please. We have 2 minutes time. So, although if there is no question, I want to give a comment that after Dirac equation, Ettore Majorana formulated Dirac equation in a different style that it should be completely real. By choosing 4 set of matrices, the Dirac equation is made real, completely real. Then he interpreted that once it is real, psi should be equal to psi star. It will be self-conjugate. This is how Majorana neutrino, Majorana particle. But recently there was a series of paper experiment that any quantum equation should be complex, not real. So I don't know how far it is true, but it is going on. If it is true, concept of Majorana neutrino and Majorana fermions will go away. That is what I learned, but it is in my field. I don't know much about. It is my comment. Anybody? Professor Haridas or anybody? If there is no question answered, let us thank our Professor Paresa, and let us pass to the next speaker, Professor Manmohan Gupta, please. Professor Manmohan Gupta. Professor Alok?
Yes, Professor Manmohan Gupta, I see him. I don't know if he's hearing us. Okay.
I think he's muted.
Yeah.
Professor Gupta, you are muted.
Am I audible?
Yes, you are.
Should I start?
Yeah, please start. Please start. We can hear you.
Okay. Okay. Good morning, everybody. Okay. First, let me express my gratitude. I'm grateful to Professor Alok and dear Gargi for giving me this opportunity to express my deepest regards and gratitude to my Guruji, from whom I have learned, learned so profoundly that it helped me to navigate through my research career in a very effortless manner. So again, I would like to express my deepest gratitude to Professor A.N. Mitra. So let me say that it was Professor Mitra's conviction at that time, that means it means late 60s and early 70s, when he considered that quarks are fundamental particles, when most of the people didn't believe that these are fundamental entities. Now this allowed us to do a lot of calculations of hadronic matrix element, which had deep implications for the quark model as well as the pattern model. In fact, I spent my time with Professor Mitra from 73 to almost 78 end. So I spent about 5 years with him. So see, one would say that his conviction, particularly regarding his idea regarding that the nucleon is not only belongs to the 8th representation of 56 representation of SU6, it is a mixture of 70 as well as 56 representation of SU6. This was very profound idea. In the sense, it allowed us to do a lot of calculations regarding hadronic matrix element, in particular about photohelicity amplitude and neutron charge radius, two very, very important. In fact, Feynman, just Dr. Dayanand Parashar emphasized, Feynman was also interested in quark model. And in 70, he wrote a very famous paper referred as FKR, where he had emphasized the importance of helicity amplitude. In fact, using Mitra's idea, we were able to explain a lot of very difficult cases of this helicity amplitude, and that was really an important. Moreover, so neutron charge radius, neutron was a neutral particle, so understanding its charge radius was very difficult in those days. So we were able to, through Mitra's ideas, we were able to explain this neutron charge radius also. That was part of my thesis, apart from many other calculations. But very importantly, see, I use this idea of Professor Mitra's idea of this, what he called as mixed nucleon, in what is called developing a chiral constituent quark model with configuration mixing. In fact, in the late 80s and early 90s, it was realized in the deep elastic scattering experiments that the valence quarks of the proton do not carry the entire spin. They carry only 30% of the spin. This was characterized as the proton spin crisis. Not only that, there were evidence of strange quark and other kind of gluons and other things. In other sense, that the neutron and nucleon structure deep inside is very, very complicated. So we use this idea of mixed nucleon to develop this chiral constituent quark model with the mixed nucleon, and it was able to explain a lot of including this proton spin crisis as well as others. So we were able to contribute. However, see, after having learned many lessons from quark dynamics, I shifted to flavor dynamics. And in flavor dynamics, that's what I have been doing for the last two or more than 2 decades. And I would be discussing some aspects of flavor dynamics, that is phenomenological fermion mass matrix and flavor mixing. Now, basically, that's why there is slight change in my topic, and I hope the organizers would excuse me for this, because I found that my talk, it is not possible for me to cover both the aspects, work dynamics as flavor dynamics, in half an hour. I need at least more than an hour to explain both the things. So I decided that I would concentrate only on flavor dynamics. In fact, Nimai Singh is also very much interested in that, because we have been discussing about it on many occasions. So let me start with this. Can I go to the next slide? Yes. Okay, my talk would be, I will have some general observation regarding fermion mass and mixing, then some pertaining to texture zero mass matrices, texture zero quark mass matrices, and texture zero lepton mass matrices. Then this compatible texture zero mass matrix with modular symmetry, which is the very latest, and then few concluding remarks. Okay, so let us, if you look at the spectrum of the fermion masses and mixing, it's very complex, and that also shows that the problem is very complex. If you look at quark masses, they span almost, you can say that almost 5 orders of magnitude. Then the quark mixing angles span another, you can say, 4 orders of magnitude. You can see that the KVO angle is somewhat large, then the next angle is much smaller than that, and then the next angle, mixing angle, is again very, very small. So this creates what is called the, you can say, hierarchy of the quark masses and the mixing angle, and it becomes little but if you add the neutrinos also, and you can see that interestingly, the neutron mixing angles are large, or neutron oscillation angles are large compared with the quark ones, but their masses are very small. And the smallest mass could be maybe, you can say, 10 to minus 2 electron volt, or fraction of an electron volt. The sum of the masses, latest, you can say, sum of the masses given by this Planck experiment, which is 0.15. And if you consider neutrinos to be Majorana particle, then you have to add almost another 14 or 15 orders of magnitude. Now, if you look in totality, the neutrinos and the quarks together with Majorana neutrinos, it spans almost more than 25 orders of magnitude. So this problem is difficult from theory point of view also, as well as from the computational point of view also. And that is why there are not many attempts we try to discuss the problem in a comprehensive manner. That means quarks and leptons together, and doing, you can say, a consistent job of explaining both the spectrum. Most of the attempts are related to neutrinos, where the mixing angle are large. And then, of course, we do not know, right now we don't have a, you can say, idea about the smallest neutrino mass. Okay, so the pattern of quark mixing angles and lepton mixing are very different. So that adds another, you can say, dimension to the problem.
Professor Manmohan Gupta, I apologize to interrupt you. Is it possible for you to kindly go full screen?
Hello?
Professor Manmohan Gupta, could you kindly go full screen, please, if possible?
I'm not able to get you. So in order to decipher them,
your display is not the full screen. Your display is not the full screen. Please make it full screen.
I'm not able. Can you send message through cell phone?
Anyway,
hello?
Please go ahead.
Okay, so So there are experimental refinements also as well on theory also. A lot of approaches are there. We can characterize the approaches as top-down approach and bottom-up approach. Now, in the top-down approach, we have grand unified theories, string theories, and other kinds of theories. We try to, you can say, produce quark masses and lepton mass matrices, and then try to go further. But there is no, you can say, a theory which has a comprehensive, you can say, explanation for the vast spectrum of, you can say, masses and mixing angle, which I have just mentioned. So, what the best thing is, there are, of course, ways to, you can say, some solutions. Okay, so the way we would like to understand this problem is, let us go to the standard model. And in the standard model, the quark masses defined like this and this. We'll start with the quark masses. The leptons can be following the same pattern. So we find that the fermion mass matrices are arbitrary 3x3 complex matrices containing in general a total of 36 real free parameters. For these matrices to provide valuable clues for developing an understanding of flavor physics, it is desirable that the number of free parameters gets constrained. Without loss of generality in the standard model and its extension with right-hand quarter singlet, fermion mass matrices can consider to be Hermitian. It is through the polar decomposition theorem that any matrix, any complex matrix can be broken as a Hermitian and a unitary matrix, and a unitary matrix can be always be absorbed in the, you can say, right-handed singlets. These Hermitian matrices are characterized by 18 free parameters. Again, the number of free parameters are large. Therefore, to start the problem to handle this problem, so Weinberg implicitly and Harold Fritsch explicitly formulated what is called the texture approach. In the texture approach, some elements of the mass matrix are assumed to be zero, and then we proceed further with that. For example, in the Fritsch ansatz, this is how the Fritsch ansatz MU and MD were assumed. And if you look at the structure, a particular structure is said to be texture N0 if it has n number of non-trivial trivial zeros, that is the sum of the number of diagonal zeros and half the number of the symmetrically placed off-diagonal zero is n. For example, this structure, this is texture 30 and this is texture 30. Together, they would be called texture 60 quark mass matrices. So this is how they started with reducing the numbers. No, the point is that if you follow this kind of approach and then try to calculate, and anyway, texture 60 was ruled out. But if you go to higher texture 50 and 40, the number of possibilities become very, very large. In fact, there are almost 576 quark mass matrices which have to be individually analyzed and then try to see whether someone follows the data or not. So therefore, this approach has its own limitation. So we decided that we should try to proceed further in a more general manner. So what we did, these are some of the publications on which my rest of the presentation is based. There are some review articles, including one by us, and there are two by Harold Fritsch and Zing. So then these are some of the latest papers on which our presentation. Now, if you, we try to use what is called a weak basis transformation. So the standard model allows a weak basis transformation without any loss of generality. So if we can take a unitary transformation and apply it on both upside as well as downside mass matrices. Now this doesn't no, a weak basis transformation, the gauge currents remain same and the CK matrix would not change, but there would be some changes in the quark structure. So it has been shown that the weak basis transformation, like you have a unitary transformation W, which acts on both the MU and MD, and using this transformation, it has been shown that the mass matrix can be either in this form or in this form, where this is shown by Fritsch, where the 1, 3 and 3, 1 element is both zero, the all other elements are non-zero. We follow this approach. It is because using this approach, we can have exact diagonalization of the mass matrix. Now the weak basis transformation preserve hermicity, as well as you can say that one doesn't have to deal with large number of possibilities. One has to deal only with those possibilities which are compatible with the weak basis transformation. So that is what we try to do. Now, this is very general. There are no constraints. So if we start with this kind of mass matrices, we can proceed further for doing the calculations. And see this this 0 at this point, it can be at this point also, and it can be at this point also. Like this is what is mentioned, that we can have 0 at 1, 3 or 3, 1, 1, 2, 2, 1 or 2, 3. So they are all possible cases. So this increase some of the cases, somewhat, there are 4 possibilities of cases, but not beyond that. And then, of course, there are other possibilities related to the basic 4 possibilities. Now, what we do is that in order to, you can say, simplify the calculation, what we do is we constrain the parameter space available to the elements of this mass matrix. We can consider the following hierarchy: natural mass matrices for the elements of mass matrix, as shown by Pichai and Wang, Gupta and Ahuja. So in fact, Pichai and Wang had shown that there has to be some constraints on the elements of the mass matrix so that you can say it remains compatible with the CK matrix. Otherwise, if you violate these, then it becomes very difficult for the mass matrix to be compatible with the CK matrix, which is again hierarchical. So if we calculate for doing it, I would not get into too many technical details of the calculation. The way we proceed is we separate the phases and the real mass matrix, and then go ahead with the you can say we construct the you can say transformation, diagonalizing transformation. Now, diagonalizing transformation has some implication in the sense that there are square roots, so they have plus minus sign. The phases have to be chosen in a very carefully selected manner. Otherwise, it becomes difficult to follow. And then this becomes mutually exclusive. The other possibilities of phases do not fit the data, so they are ruled out. So we have chosen those kind of phases, and then the CK matrix is constructed. And then, of course, we use this quark masses at the MZ scale, and then of the quark mixing parameters, or you can say CP violation parameters. This sin to beta represent the CP violation, and other, of course, the normal 3 mixing angles. So we, unlike Wolfenstein parameterization, we follow different parameterization. We believe, and we have written 1 or 2 papers also, that the PDG representation is more suitable for when unitarity has to be preserved, unlike the Wolfenstein parameterization, where unitarity has to be proved order by order using the parameter lambda, which is the Cabego angle. So if we continue with this thing, and the parameter 5 and related phases of the quark have been given full variation, EU, ED have also been given as with the condition of naturalness, and then we construct this matrix. And then obviously this is fully in agreement with the PDG, because there are a good number of parameters in the theory, so it has to agree with the PDG representation. So therefore, our next step is, no, what about, this is the mass, these are the mass matrices. You notice that of course, this CP violating J comes out in the right amplitude. I should also mention something about this J parameter. In fact, back in 1999, we were the first to calculate this J parameter, and using very raw data, we could predict, and that prediction still is valid. Of course, it had larger number of errors. I talked to Cecilia Jalskog also, and she was also quite impressed. Somehow or the other, it is not neither mentioned by PDG nor by many other people who work in this area. But we were she acknowledged that our paper was much earlier than many other papers. So we introduced that this J parameter is very important for calculation of CP violation effects in this CKM paradigm. See, if you look at the mass matrices, this element 1, 1 in both is very small. So obviously we wanted to see whether if we ignore this element and proceed further, what is the effect of that? To that end, we, for example, first we try to see the, like if we plot this EU and E. E is this is the first element, and we find that with respect to sin to beta and Vs, we find that the dependence, there is no dependence of VUS and sin to beta on EU. That means if we ignore this element, hardly it will make any difference to the calculation. So we ignore for both MU and MD this element and then redo the analysis. And what we find is that the CK matrix again comes out to be right. the CK matrix, the values agree very well with the, you can say PDG data. Therefore, what we have done, we have reduced the number of parameters from texture 20, we come down to the texture 40 mass matrices. Now, if we are texture 40 mass matrix, then obviously there are other representations, other possibilities which we have to consider. So there are 4 possibilities. This is 1, 2, 3. First, we have already considered. So these other elements are related to permutation symmetry, which is a unitary matrix, so it doesn't have any independent consequences. So out of the 6, we have to consider only 1 also. This we have already considered. Now, this line, if you look at it, the third generation is decoupled. And if you have a decoupled 3D generation, we will not be able to reproduce data. Therefore, again, this can be easily discarded. The other 2 categories, 2 and 3, we have done the analysis, and what we find is these are also ruled out in the sense that if you look at the VCK matrix, the VCB value comes out very large in both cases. In fact, this is the graph also shows this thing. The VCB value is much larger than what is the current expected value. Therefore, these 2 possibilities are also ruled. Hence, we are left with only one possibility, which is very near to the what is the Fritz-like mass matrices, where if you look at it critically, what one finds is that except the 2 element, the other structure is similar to Fritz-like. But see, this is as far as the phenomenological analysis is concerned, we have not been able to show, nor anyone else has been able to. This is the only unique possibility. We are still working on it and hoping that we'll get some clue. And later on also I'll mention that discrete symmetry and modular symmetry may provide some clues in this direction. Now, same thing can be carried out for the texture 0 lepton mass matrix. There are a lot of analysis, large number of papers, mostly you can say in the flavor basis. In the flavor basis, we take the ML and the lepton mass matrix to be diagonal and a neutrino mass matrix to be non-diagonal. But we have tried to consider using quark-lepton symmetry, that if at all we have a theory which predicts both quark and lepton, there has to be symmetry between the 2. So if we try to consider the Hermitian 20 and 40 quark matrices and try to, and assuming neutrinos to be Majorana particles, we have carried out the analysis and some very interesting results have come out. I will not try to get into, you can say, too many results, discuss too many results, but I'll just mention some very important results which we have obtained with this analysis. So this is, of course, the PM-NS matrix, which is really reproducible. Now, what we find is that in the case of, if we consider the inverted mass ordering and the normal mass ordering, the predictions are very different regarding what is the element MEE, that is which measure the, you can say, the possibility of neutronless double beta decay. And what we find is that in the case of inverted mass hierarchy, there's no, it's almost as far as these are the phi's, and if we calculate, this is of course the smallest quark mass matrix. Then if we vary with the M3, then the result do not change much. So this is the prediction of the, you can say, in the case of inverted hierarchy. But if you go to in the case of normal hierarchy, what we find is that the results are very interesting in the sense that there is a dependence on the phase factors also, that is a CP violating factor, as well as, no, this is the smallest neutrino mass, M1. Now, what we find is up to this point, that is for M1 from 0.01 to 0.1 electron, the bond on parameter 1 gets sharpened on 1 obtains ME within the band. This is the, now, if the neutrino mass is in this range, then we get, this is the MEE value. And whereas for M1 greater than this this value, 0.01 electron volt, then one finds that there's a broader spectrum. So the predictions are very clear as far as the element ME is concerned. This is for texture 20. But if we go to texture 40, no, there is a very sharp prediction. And that prediction is, you can see that the M1 and ME is confined to very small. So I am sure that in particular careful comparison plot showing parameter ME for texture 20 and texture 40 normal ordering reveal that the case later on obtains very limited region of viability. Texture 40 shows very limited region of viability. Therefore, non-zero values of one elements, the neutron mathematics has to be significantly different predictions as can. See, in the case of neutrino, we cannot go from texture 20 to texture 40 because the one element has a lot of dependence. And it is because the neutrino mass spectrum is very different. So therefore, we can't go from 2 to 4. However, if we assume that the one element is not there, and that is why the predictions become very sharp. So if by any theory we are able to show that the quark mass matrices as well as neutrino mass matrices of texture 40, then we have very sharp predictions and which can be easily, which is going to be tested in the coming, you can say this is the further range of lightest mass severely constrained. So this is the range of the lightest neutrino mass M1 in the normal hierarchy if we have texture 40 lepton mass matrices also. So we have used this is as far as the this quark mass matrix is concerned, and quark mass matrix is considered unique viable option for description of quark mixing data. And for neutrino, there is a prediction for ME, for NO as well as for the normal hierarchy as well as for inverted hierarchy. Now, see the next question. I have not gone into details of that. Now, obviously, the next question arises: how do we, you can say, reproduce this quark or texture specific mass matrices? There are a lot of attempts, including discrete symmetries. So in fact, we have also worked on S3 cross Z3 model, but somehow or the other, it is not easy to reproduce the model. However, a similar kind of model one is able to get. And of course, that model is able to fit the data, but I am not including in this. But lately, what we find is that the modular symmetry lately has given a new gateway for explaining this fermion masses and mixing. Now, this has some inherent advantages, and modular symmetry, I will not get into the details, and we are still working on it. We have not arrived at any specific texture structure, but we are almost near that. And this, I'm sure that those who are working on it, they understand how this modular symmetry is defined. And then, of course, this is how we obtain the y functions, and this is the gamma functions. The gamma function, it corresponds to, for example, the modular symmetry incorporates discrete symmetry, like gamma 2 is S3 and gamma 3 is A4. So a lot of analysis is being done using this gamma 3 and A4, gamma 2 S3. Also, we are particularly interested in S3 cross Z3 model because we had some experience with doing calculation in the using the discrete symmetry of S3 and Z3. Those calculations are still we are doing. No, this is that means this is compatible, and this is the structure which we get using S3 cross Z3, and this is as far as this is compatible. This is again texture 20. So this is compatible. I am sure that we still have to carry out a detailed analysis of that because there are some issues. I am sure there are some issues about what is called this is Dedekind function. See, the numerical values of Dedekind function I find is different given by mathematician, by string theories, and as some people who have tried to use this fermion masses and mixing. So their values are not coinciding. We are working on that what is the best value to be used for the calculation. Only then there is some kind of, you can say, emphasis in the calculation. No, so there are some advantages of modular symmetry. I think the most important is that this is directly from mathematical framework and dimensional compactification of string theory, hence is more reliable than any other existing theory. Or in other words, it is very much compatible with the string theory. So therefore, whatever predictions one makes in this modular symmetry, I think the other important factor is that the hierarchy is built into the y functions. And that is very important. The y function, the symmetry has already hierarchy in it. So one doesn't have to add what is called flavanones, or you can say additional, you can say scalar particles to provide hierarchy in the fermion mass matrix. So anyway, I have covered some ideas And with this, I would like to conclude and again re-emphasize that the lessons learned by a smaller person like me from Professor Mitra's interaction, they were really profound. And it has helped me in not only uh, getting into new areas, but keeping me always active, taking inspiration from me. I remember that even about I think about a decade back or maybe earlier than that, I had met him and still working, and he was publishing papers. And I remember that he had mentioned that he had written a paper on three body forces. So his mind was active, he was physically active always. So I always long to have that kind of inspiration instilled in people like us so that we keep working and keep enjoying his legacy. Thank you very much for listening to me.
Thank you, Professor Manmohan Gupta. It is almost 30 minutes, but we can entertain one question at least as a
Yeah, sure, please.
representation. One question at least. Yes, please, sir. Please, please. No sound. You please put us.
Second.
Oh, yes.
This modular symmetry seems rather ad hoc. What is the dynamical justification for that?
Yes, right.
Could you, Dr. Nemaisi, repeat it because I'm not able to hear him.
No. I will repeat. The modular symmetry used in neutrino physics is ad hoc. What is the justification?
Again, I am not able to. And maybe you can mail this question. I will send the reply maybe today itself. So
Yes.
you can send the question to me through mail or Nemaisi, you can send through this WhatsApp message also. I will
Okay,
send through email, right? I think
Thank
there is
you.
some problem about audio at my end. So that's why I'm not
So,
able to hear others that well.
so by
Can
using
I ask a
so,
question?
Okay, I think the best thing is that I've almost utilized the time. So whatever questions are there, they can be mailed to me. I'll send the email reply to either Nimai Singh or I will send it on the WhatsApp, right?
Okay, sir, Professor Haridas, is it okay?
Fine, wonderful.
Okay, now it is time up. So let us give the thing to the next speaker, Professor Tirupatur Venkata Sala Murthy Ramakrishnan. Okay, so let us give pass to the next speaker. Thank you, Professor Manmohan Gupta ji.
Okay.
Professor Gupta, could you kindly unshare? I think, Professor Ramakrishnan, if I'm
Yes.
audible, would you want us to take care of your slides or would you?
That would be better, yes.
Excellent.
Thank you.
Okay. Well, just give me a second, please. All right, Professor Ramakrishnan, I pray
Yes, please.
the slides are visible, first page.
Oh, absolutely. Everything is visible.
Excellent.
Am I audible?
And could you just let me know when to go to the next slide? Just say next, we'll go enter to the next slide.
Thank you. Yes.
Thanks so much. Thank you.
Yeah. Thank you very much. I'm actually very grateful also to Professor Alok Mishra for organizing this meeting and for asking me to participate in it. I'm also very thankful to Professor Nimai Singh for taking the pains to spell out my full name. And that itself shows why it is not desirable to use it often. It is used in my passport, yes, but I almost never use it anywhere else. Thank you very much. Can we go to the next slide, please? Can we go to the next slide, please? Yes, thank you. You see, for people of my generation, for physicists of my generation, Professor Mitra was an inspirational figure. And his personal example as a physicist and his values in physics and his ideals were something which motivated many of us. I realize that I'm somewhat of an odd man out in this gathering because I'm not his direct student. I'm not a particle physicist. I work in another subfield of physics. I would like to talk a little bit about some recent work which I have done with two colleagues in this field. Before that, I would like to share two reminiscences of Professor Mitra. One is the following. I think sometime in the mid-1990s, I became aware that Professor Mitra, after retirement, was actually staying for a short while in the Institute of Advanced Studies, which at that time was directed by Dr. Raja Ramanna. I very quickly contacted him and requested that his unique knowledge be shared with students. And I arranged for a course on nuclear physics to be given by him in the Indian Institute of Science, which happened. And that was the formal connection. But then since actually our contact goes back to that with his father and my father-in-law and so on, there was a lot of personal interaction. Secondly, I came into close contact with him when he was editing a book which was mentioned by Professor Panchapakeshan, which is on India's contribution to physics, which is a part of a huge multi-volume enterprise by Professor Chattopadhyay on the contribution of India to history, philosophy, civilization, science, etc., etc. In this context, Professor Mitra suggested that I should write an account of the Indian contribution to condensed matter physics, which I was happy to do. And this went on for actually several years. And finally, it was published. And as Professor Panchapakeshan said, it is well buried. I mean, it's hardly anyone knows about it and knows about the book because it's an extremely expensive book, which is in many volumes and not very easy to access. But that association was very important to me because it came at a very important stage in my life. Now, what I would like to do in the next several minutes is to talk about some preliminary work on a possibly paradigmatic limit of the behavior of electrons in metals. In this limit, electrons are actually mobile, they move around, so they are globally free, but locally they are very unfree in the sense that if two electrons happen to be nearby, then the repulsion between them is extremely strong. Now, in order to sort of motivate this limit, I would like to start with the opposite limit, which is the free electron limit, which almost all of us are familiar with. Could we go to the next slide, please, Professor Mishra? Yeah, thank you. Well, this is a limit which was proposed in 1900 by Drude. It's a very extremely unreasonable proposal. He proposed 3 years after electrons were established to be a common constituent of matter, that metals consist of a free classical gas of electrons. Now, this is extremely, I think it's hard to believe because, it was clear to everybody, including him very strongly, that electrons are very strongly tied to the parent ions from which they originate. They also
interact with each other. The Coulomb repulsion is not switched off. And therefore, to regard them as free is somewhat unrealistic. Not only that, it was not clear which electrons were to be considered free, which were to be considered unfree. But he argued that maybe the valence electrons should be considered as free because they enter into chemical bonding. Now, with this extremely simple hypothesis of assuming that all the valence electrons in a metal are to be considered as constituting a completely ideal classical electron gas, he was able to successfully explain many electrical and optical properties of metals, including using the kinetic theory of gases idea, except that in this case, the elementary constituents, the particles are charged. He could explain Ohm's law, he could explain skin effect, and what at that time was considered a very great success. As a matter of fact, Albert Einstein thought that this was the greatest success of this Drude picture. He was able to show that a particular ratio of thermal conductivity to the electrical conductivity divided by temperature is a universal constant. This is called the Wiedemann-Franz law. This universal constant for for an ideal quantum gas is known to be pi square by 3 kb square by e square. But he was, of course, a generation before the quantum revolution, and he got 3 by 2 kb square by e square in classical, using using the ideas of a classical gas. Now, this ratio is almost right, partly because two factors of the order of 100 cancel each other. And also, I think because at that time, the electron charge was not particularly reliably known. Electron charge was known to an uncertainty of about 20–30%. So that gave an error of about factor of 2. And with all that, he was able to compare his this number with the experimental value, and it turned out to be in fairly good agreement with what was known, and it was considered a great success of the theory. So let me go to the next slide, please. Yeah. Now, this kind of approach has several problems, some of which I mentioned. One of them is that we don't know which electrons are considered to be free. He assumed that these are valence electrons. Now, of course, we know that, yes, these are electrons in the unfilled shells, and these are indeed valence electrons or holes. He also assumed that these electrons form a classical gas. We know that, they form a degenerate quantum gas of fermions. If you assume a classical picture, which he did, which he had to, then you find that the specific heat from the Dulong-Petit law is proportional to the Boltzmann constant. Whereas in reality, if you assume it to be a quantum gas, it is proportional to the Boltzmann constant times T by Tf, and this is indeed what is observed. The most worrisome problem was the pretense that electrons don't interact and form an ideal gas. They actually interact with the lattice ions and with each other. And there are many very sophisticated, adiabatically connected, successful theories of interacting electrons with interaction effects, which are described by a few parameters like the effective mass and so on. So this is the Fermi liquid theory of metals, which is the canonical theory, which we use all the time. Can we please go to the next slide? Yes. So it is now believed that electrons in a metal form an interacting Fermi liquid. This is not a Fermi gas. This interacting Fermi liquid is a coherent Fermi liquid for temperatures much lower than the Fermi temperature. It has well-defined quasi-particles. It has well-recognized collective excitations. It has a superconductive instability for effective electrons between these effective attraction between these quasi-particles. Now, that is where matters stand as far as this limiting paradigmatic behavior picture of electrons in metals is concerned. However, it turns out that there is a large class of systems and phenomena in metals where the interaction between the electrons is the dominant thing. That is, the repulsive potential energy of interaction between the electrons is much larger than the kinetic energy of electrons. But in spite of the fact that this is so, the thing is a metal with mobile and kinetic electrons. So there are many ways of putting it. You can say that electrons move while strongly avoiding each other. You can say somewhat more formally that these are strongly correlated electron systems and so on. So the obvious question is there an opposite paradigmatic limit which is natural for such a system in which electrons are locally unfree but globally free? So that is, see, if the interaction between the electrons is very strong, then you cannot treat it as a perturbation on the motion or the kinetic energy of the electrons. So is there a non-perturbative limit which we can use, which is also metallic? Well, I will describe a tentative attempt to understand and describe this limit in a lattice model for electrons. This is work which I have been doing with Professor Hassan of the Institute of Mathematical Sciences in Chennai and Professor Vidyadhiraja of JNC in Bangalore. This was published last year, the first paper. Can I please go to the next slide? Yeah. And now, to start with, of course, we start with the Hamiltonian. Well, the Hamiltonian is written there. It is the energy of an electron which is sitting at a lattice site I, when it has spin sigma, it has energy epsilon I. For a homogeneous system, epsilon I does not depend on I. It is the same at every site. If two electrons happen to be on the same site, and from the Pauli exclusion principle, they have to have opposite spin, then they repel each other with a strength U, which is positive. U can be small or it can be large. The kinetic element, the motion of electrons, is provided by the fact that an electron from a site I can hop to a site J and vice versa. So this is known as the tight binding model of an electron system. That is, you have the electron tightly bound to the lattice site, but hopping quantum mechanically from one site to another. The U is an oversimplification. The fact is that the effective interaction between the effective Coulomb interaction between two electrons in a metal is short-ranged, because though the bare interaction is long-ranged, the effect of other electrons is to screen this bare interaction and make it short-range. So we go to the opposite limit. We assume that this interaction is zero range. That is, unless the two electrons happen to be on the same site, there is no interaction. And this is somewhat of an oversimplification, but it turns out that we can't solve this model either, because even though it looks very simple. Can we go to the next slide, please? Yeah. So this model is extremely well known. It is known as the Hubbard model. It is actually exactly soluble in one dimension, and it's also exactly soluble in all dimensions if the interaction is zero. Interaction vanishes. When the interaction vanishes, you have a collection of independent electrons, and this is just what I said. It's a tight binding version of the free electron gas. Now, if the interaction is non-zero, and if you treat the effect of this interaction as a kind of a perturbation on the kinetic motion caused by non-zero Tij, then the substance is a metal at all filling. But this cannot be always right. For example, suppose the filling were half, that is, suppose there were exactly 1 electron per site. Suppose the electron density is such that there is 1 electron per site. Now, if the repulsion between the electrons is very large, then it is energetically favorable for electrons to stay at their sites and not move. And such a thing is an insulator. So the ground state is an insulator. Such an insulator is known as the Mott insulator. This has a qualitatively different many-body wave function. But then you can ask the following question. This is actually a very different but a somewhat simple limit. But suppose the filling is not half. That is, suppose you don't have exactly 1 electron per site, which means that there are some sites which have electrons and some sites which do not have electrons. Then it has to be a metal, because an electron can always find a neighboring site which has none, and so can hop to it, and so on. So then the question is, what kind of a metal do we have in that case? And all experimental facts point to its being a somewhat strange metal. It has a characteristic coherent Fermi liquid behavior at extremely low temperatures. On the other hand, it is an incoherent Fermi liquid over a very wide range of temperatures. And how does this incoherence manifest itself? It manifests itself in the fact that there are no quasi-particles. That is, if you have a particle of a given momentum, momentum is a good quantum number within the Brillouin zone vector, modulo the Brillouin zone vector. If you have an electron with a well-defined momentum, it should have a well-defined energy. It turns out that this is not true, but if it were true, then the spectral density would be a delta function. In reality, the single particle spectral density is very broad, so there is no quasi-particle. Another experimental feature which is very odd is that a clean metal in this family has a resistivity which is linear in temperature. Now, it turns out that clean metals which are Drude-like, they also have non-zero resistivity. Like, copper has non-zero resistivity, platinum has non-zero resistivity at non-zero temperatures, and so on, even when it is very clean. And that is due to the interaction between the electrons and the lattice vibrations. Here, that resistivity is most likely very small, but in spite of that being so, there is a very large linear in temperature resistivity for clean systems. This particular feature has been very extensively studied in cuprates, and recent experiments are unearthing more and more strange aspects of this linear resistivity. So what have we done? We have tried to see whether this incoherent Fermi liquid regime can be explored in an opposite limit. That is, whereas in the Drude free electron limit, you are essentially assuming that the electron repulsion U is 0. Let us see whether we can do something about describing in a generic way what the behavior of the system is when the interaction between the local repulsion between the electrons is infinitely strong, that this is the opposite limit. So it's not clear at the moment whether we can do it and whether we can say that this is a paradigmatic limit, which is an unfree electron limit relevant to the large family of strange metals, and so on. Well, that's our aim. I will describe a tentative approach to the infinitely strongly correlated electron limit. Please go ahead. Yeah. To describe this limit, we use a very simple representation, which was again due to Hubbard, which is called the Hubbard X operator representation in this subfield. Basically, you have at a particular site I, these Hubbard operators XIAB, where basically the this operator is this ket times this bra. The complete set of states at each site is given by what A can be. A can be 0, 0 meaning no electron at that site. Up meaning one up spin electron at that site. Down meaning one down spin electron at that site. Now you cannot have at this particular site a state in which both up electron and down electron live together. If U is equal to infinity, then that is infinitely high in energy, and therefore it is removed. So there are only 3 states possible per site. And so you have a lattice, you have a space of states in which at each site there are 3 states, and you have a product of all this. So the Hamiltonian is an operator which lives in that space of states. What is the Hamiltonian now? That also we simplify. We assume that it costs 0 energy to occupy an electron state. So epsilon is 0. Mu is the chemical potential. This is the only variable in the system, actually. Depending on the value of the chemical potential, you have the occupation number varying from 0 to 1. Occupation number meaning the average fractional electron number per site, average. It is not the electrons are fractionated, but this can be any fraction. This average can be any fraction. Then you have a hopping. So this describes the hopping. Describes the hopping from a state sigma at site I to another empty site state at site J, again with the same spin. So this is an extremely simple Hamiltonian, and it would have been exactly soluble if this were a canonical fermion creation operator. Unfortunately, it is not. And so this cannot be solved. This has not been solved exactly, and we are still struggling with how to solve it. We simplify this even further. We say that the hopping is non-zero, an electron hopping is non-zero between one site and another, only if these are nearest neighbor sites. This is simply because hopping is via the overlap of quantum mechanical wave functions, and the wave function overlap is becomes rapidly very small as distance increases, and therefore the only sensibly non-zero, essentially non-zero, unavoidably non-zero overlap which has to be included is between nearest neighbors. So it's actually, so this model is characterized by one energy parameter and actually 2 energy parameters, but this energy parameter is basically related to the occupation number. Now, there is, as I said, there is no small parameter in this theory. There is no perturbative expansion. Now, this model has been studied actually in great detail by Shriram Shastri starting 2010. Using the Schwinger source method. That is, he adds to this Hamiltonian a source term and then takes various derivatives with respect to the strength of the source, and then finds different kinds of coupled equations for Green's functions, and then reduces the source strength from 0. Okay. So there is a whole set of papers. There are, I think, at least 700 pages of papers, starting with this, and then also one more recent version is in 2022. What we have done is to study the same Hamiltonian in a slightly different method. We use what is called an equation of motion method. That is, we find the equation of motion for different correlation functions like XX correlation functions, which could be fermion correlation functions or boson correlation functions and so on. And we use the infinite dimensional approximation. This is a very successful and defensible approximation for real systems, which are of dimension more than one. We use this approximation to decouple the equations of motion for Green's functions, and then we solve these equations self-consistently. Can I have the next slide? Yeah. So the crude physical idea is the following. If an electron moves, then it necessarily gives rise to local bosonic fluctuations. This is what I have tried to show here on the right-hand side, where I have showed that suppose an electron hops from one side to the next side, then at this side, the electron number changes or the spin changes, and therefore there is a bosonic fluctuation produced here. And then at the next side, the next nearest side, the electron is there, and therefore there is an electron, the electron propagates there. So basically, we say that the electron motion gives rise to local bosonic fluctuations, and the propagation of bosonic fluctuations depends on electrons. And for this purpose, for this reason, self-consistently finding the correlation function is very crucial. And which is what took us a long time. It took us almost 2 years. So I will just present some results. One of the results is the following. We have calculated, for example, the single particle Green's function of Green's function. Its self-energy, the imaginary part of its self-energy for small energies or frequencies should go as frequency squared. That is a signature of a coherent Fermi liquid. We do find that that's what happens. For example, this inset shows the plot of the imaginary part of the self-energy as a function of frequency for different dopings. You can see that at extremely low frequencies, it is parabolic, that is proportional to omega square, but then very quickly it becomes linear. Here we have shown also the real part of self-energy, which ought to be linear, which it is if it's a quasi-particle. So the behavior of imp sigma as omega square, behavior of real sigma as omega for small omega is a signature that you have quasi-particles. And you actually do have quasi-particles at extremely low temperatures and extremely low frequencies. So let me go ahead, please. If I have the next slide, I can show more. So, you know, while obtaining this result, we found that there are sort of inevitable local bosonic fluctuations of local charge or local spin with which the electrons are coupled. I have shown here the spectrum of local bosonic charge fluctuation at a doping, I think, of 0.2 or so for different frequencies and temperatures. You see, at the lowest temperature, it's extremely sharp. As the temperature increases, this bosonic fluctuation becomes somewhat broader. It is highly asymmetric. It has a sharp rise followed by a rather broad, gentle decay. Now, this is an intrinsic bosonic fluctuation spectrum, which can be identified as a kind of an intrinsic quantum noise in the system. So let me go further. Please go ahead. Next slide, please. If I can have the next slide. Yeah. So this fluctuation well, it doesn't look like anything which we know. In the sense that it is not it doesn't have a simple form. We have tried to fit it to a kind of a Lorentzian form, but it has a much longer tail than a Lorentzian. So we have tried to wrestle with this local bosonic fluctuation spectrum in many ways. One of them is to calculate the mean energy. So you calculate the mean energy of this fluctuation, which is omega, and we show it as a function of temperature here. Omega is on this side and temperature is on this side. By the way, all energies like omega, T, and so on, they are shown in dimensionless numbers. The dimensionless number means this energy is divided by another energy, which is the hopping energy. Now, what we see is that at low temperatures, the mean energy of bosonic fluctuations is higher than the temperature. So we, using a naive identification, which is very common, we say that this is the quantum regime where the mean energy of these fluctuations is much larger than the temperature. We find that yes, there is a regime where the mean energy of fluctuations is larger. Then at a higher temperature, it becomes smaller than the temperature. So we show that result in the next slide. Can we have the next? Yeah. So here you see that the three regimes, one which is confined to extremely low temperatures, where the imaginary part of self-energy and the real part of self-energy are those which correspond to a canonical Fermi liquid. That is shown here, the Fermi liquid regime as a function of doping and temperature. You see that it is there at all dopings, but at extremely low temperatures. Below this temperature, it is a Fermi liquid, and above this temperature, it's an incoherent quantum liquid. We call it incoherent quantum regime. As you increase the doping, this temperature increases, and above this temperature, you have what is called the classical regime. In this classical regime, it is easy to describe qualitatively the goings on. You can say that, well, in this classical regime, each electron is basically not hopping. It is sitting at a particular site. And if there are, let us say, 0.6 electrons per site, then 0.4 sites have no electrons, and 0.6 sites have electrons, either of upspin or downspin. If the system is paramagnetic, the number is equal. And obviously, if you have a lattice, there are a large number of arrangements of this kind, and that gives you the entropy of the system. So this entropy is also very well known, and if you can calculate this entropy. So this is an entropy of charged systems, and therefore it should be relevant in thermopower. And indeed, it turns out that in strongly correlated systems, the thermopower reaches this classical limit at surprisingly, astonishingly low temperatures, and the value which it has is roughly the same as what you would have if you assume the electrons to be classical, non-hopping, strongly correlated objects, 1 electron per site. Yeah, can I have the next slide, please?
Sir, please wind up. So 10 minutes more.
Okay, oh, I'm running. Okay, then I'll wind up. So let me just wind up by saying that we have also calculated the resistivity. We show that the resistivity is T square at low temperatures. It is linear at most other temperatures. There are two regimes. This is one linear regime. There is another linear regime. There is a crossover. Let us go ahead. And we don't understand this either. Let us go ahead. Yeah. Next slide, please. Yeah, so we believe that we have unearthed two crucial features of extremely correlated Fermi liquids. One is strong local diffusive self-generated bosonic fluctuations coupled to electrons, and another is a large incoherent quantum regime. We do not know what the origin of this extremely low temperature is. The theory is extremely opaque. It is very complicated. We need a simpler, clearer theory. We do not have it yet. This is for a u equal to infinity. Unfortunately, all systems have finite u. And even the strongly correlated systems in which u is very large, by which I mean u by t is larger than 10, u is finite. So we have not yet developed, and we are at the moment we are in the process of developing a theory which is of first order in 1 upon u, that is first order in t upon u, which is a small parameter. Please go ahead. Next slide, please, and I think I'm done. Yeah. So we are generating this, trying to develop this 1 upon u perturbation theory. We know that there is a 1 upon u expansion which eliminates the high energy excited states, and so there is an effective low energy theory which is correct to order 1 upon u. Not an easy theory, and we don't know what to do with it. At the moment, at least we don't have any concrete results. However, many years ago, we had developed a phenomenological theory with, that is we meaning here, Sumilan Banerjee and Chandan Das Gupta and myself, which seems tantalizingly close to what one expects of this 1 upon u theory. Thank you very much.
Okay, we can have 1 or 2 questions or feedback. So please, from the audience.
Is it okay, Professor Nima, if I could ask one question?
Please.
So, Professor Ramakrishnan, this may be a not very well formulated question. I apologize in advance. But what I was wondering was that are there, I mean, it may not be even directly related, but it basically hinges on this idea of dealing with the non-perturbative systems or working in the non-perturbative regime. So I was wondering, are there any kinesimatophysik systems which have, dare I say, a u going to 1 over u symmetry or a modular symmetry involving u? Is it a strong weak coupling duality? Any system in kinesimatophysik which has strong weak coupling duality as a symmetry?
I think the Kondo effect, for instance, is a kind of a model in which, as you change the energy scale, there is a logarithmic increase in the effective coupling constant, and it becomes an extremely strong coupling system at very low temperatures, which is somewhat like gauge theory of strong interactions.
I see. Thank you.
Okay. Any more question? Otherwise, we can thank the speaker. Or any question? Other?
Professor Panchpageshan has a question.
Please.
Yeah, I have a question which is not closely related. What happens to things like Anderson localization when you consider these kind of theories?
Yeah, this is a theory for all right. Anderson localization is something to do with a strong disorder effect, effects of disorder. This is for a very clean lattice system, in which a homogeneous clean lattice system. So that's the lawyer's answer. The real answer is I don't know. Also, that generally people believe that if there are strong correlations, localization effects will be enhanced.
Thank you.
So now we have, let us thank the speaker, Professor T.V. Ramakrishnan. So we have completed 6 talks given by 6 eminent speakers. Let us once again thank all of them, Professor N. Panchpageshan, Professor I.S. Mani, Professor N.D. Haridas, Professor D. Parasar, Professor M. Gupta, Professor T.V. Ramakrishnan. We conclude this session with a big thank to all our participants in online mode. And now I pass the session to the organizer, Professor Alok Mishra. We may meet around at 2:45 once again. Thank you.
Right. Yeah. Thank you so much, Professor Nimai Singh. So indeed, that brings us to the end of the session one, day one. And I think we're doing, at least we are exceeding my humble expectations with respect to time, and that's excellent. And so as Professor Nimai Singh pointed out, we are supposed to meet 2:45 p.m. So might I humbly request that we may start joining maybe 2:30, 2:35 onwards, so that we can actually get things moving at 2:45 to the extent possible. And so we're going to be having Professor Nivedita Deo as a chair for there are multiple post-lunch sessions. So the first post-lunch session, which is 1 hour, starting 2:45 through 3:45, is going to be chaired by Professor Nivedita Deo. So let's meet then, and thank you so much. By the way, I just want to point one thing out. Sorry, Indranil, sorry, I apologize. Just one little thing.
Yeah, please go ahead.
We are going to be using a different Zoom link for the post-lunch proceedings. So please do remember to do so. And another thing is that the last word as regards any update is the website. So if you click on any link, that can be assumed to be the most updated version. There are going to be no changes, but in case there is any confusion where to join, how to join, just click on the Zoom link available at the website. Yeah, sorry, Indranil.
No, this is something important. Also, few mails were exchanged with Tony Thomas in the morning. So he probably didn't read it carefully, the link. I have sent it to him, but I think it's Adelaide time 4 p.m. and not 4:30, because his talk is at 12 noon. And so Adelaide time will be 4 p.m. So that I have confirmed with him. Our schedule shows 4:30 probably.
Oh, I see.
But he knows it. So, but okay, for the general audience who may like to attend, that they should not miss it out.
So this, yeah, right. So I think, okay. So, I mean, it is a correction with respect to his time. He's going to speak 4:30 his time. Is that right?
No, I think 4. I checked on net also. The Adelaide time is 4. It's a 4 hours difference.
Okay. So what I mean is,
IST.
as far as local time is concerned, it stays at 12 p.m.
Yes.
Okay. All right. Great. I mean, frankly, that is what we are concerned with. So great. I mean, yeah. Thank you. Thank you so much. Thank you. All right, folks. So I think we end the session. Thank you so much once again. Please do join in at 2:45, beginning close to 2:30. That's when we have the first post-lunch session today. Thank you. Namaskar. So I'm ending the meeting for all now. Bye-bye. See you soon.